Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we are listening for something very small, very far away, and very old. Not a sound in the usual sense. Not something that moved through air, rattled a window, or made a cup of tea tremble on a bedside table. This was a different kind of message. A quiet stretching and squeezing of space itself, travelling across the universe for 130 million years, until one August day on Earth, our instruments finally noticed it. The event is called GW170817, which sounds less like a cosmic turning point and more like a password someone forgot to change, but behind that plain little name is one of the most remarkable moments in the history of astronomy. It was the moment we heard two dead stars collide, and then, almost immediately after, saw the light from the same collision spreading through space. Before we drift into that story, I would love to know where in the world you're listening from tonight. Are you somewhere quiet with the lights low and the day finally folding itself away? Is it late where you are, or early, or one of those strange in-between hours when the world feels as if it is holding its breath? And if you're comfortable sharing it, what time is it in your little corner of Earth right now? It feels fitting to ask, because tonight's story is also a story about timing, a signal arriving after millions upon millions of years, a flash of gamma rays appearing less than 2 seconds after the gravitational wave, telescopes turning quickly, like sleepy owls suddenly noticing a rustle in the dark, scientists refreshing screens, checking alerts, making calls, and realizing that the universe had just tapped on the glass. If you find this journey soothing, interesting, or simply a gentle way to let your thoughts settle after a long day, I would be ever so grateful if you liked the video and subscribed. It helps this quiet little place reach other people who might enjoy learning about the universe without being shouted at by it. And tonight the universe is not shouting anyway. It is doing something softer. It is sending ripples through space-time and asking us, very politely, to pay attention. So, settle in. Let your shoulders loosen a little. Let the screen glow gently if it is still on, or let your eyes rest if they are already feeling heavy. We're going to begin with a sound that was not really a sound. A collision that happened before the dinosaurs were gone from memory, before humans, before cities, before clocks, before anyone on Earth had ever wondered whether the stars could speak. Somewhere in a galaxy called NGC 4993, two neutron stars were circling one another. They were not ordinary stars anymore. They were the crushed remains of massive stars that had lived fast, burned fiercely, and died violently. Each one was only about the size of a city, yet heavier than the Sun. Imagine taking more mass than our Sun and squeezing it into something small enough to fit across a modern city. Then imagine two of those objects orbiting each other faster and faster, dragging space-time around with them, losing energy, and slowly falling inward. That image alone is strange enough to sit with for a moment. Two city-sized stars made mostly of neutrons, dense beyond anything we meet in everyday life, turning around each other in the deep dark. If you could somehow place a teaspoon of neutron star matter on Earth, which is a sentence that already deserves a careful warning label, it would weigh billions of tons. It would not sit politely on the table next to your biscuit. It would be more like asking a mountain to fit into a spoon, and then expecting your kitchen to remain calm. Neutron stars are the kind of objects that remind us that nature is not limited by what feels reasonable. The universe has no obligation to keep things at a comfortable density. For millions of years, these two neutron stars moved together in a slow inward spiral. Each orbit carried them a little closer. Each turn sent out a little more energy in the form of gravitational waves, ripples in the structure of space and time. Think of dropping a pebble into a pond, except the pond is the universe. The pebble is a pair of collapsed stars, and the ripples are not moving across water, but through the very geometry that holds distances and durations together. It is not a perfect comparison, of course. Space-time is not a pond, and neutron stars are not pebbles. Though if pebbles could weigh more than stars and ruin everyone's afternoon, perhaps they would be closer. But the image gives us a gentle way in. Something moves, something changes, and the change spreads outward. For most of human history, we did not know that gravity could make waves. We knew gravity as the thing that keeps our feet on the ground, pulls rain downward, gives weight to blankets, and makes getting out of bed feel slightly more ambitious than expected. Newton described gravity as a force acting between masses. Einstein later showed that gravity is better understood as the bending of space-time by matter and energy. A planet moves around the sun not because an invisible string is tugging it in circles, but because the sun has curved the space and time around it, and the planet is following the path laid out by that curve. This is already a big idea. It asks us to picture space not as an empty stage, but as something flexible, something that can be shaped. Einstein's theory also suggested that when massive objects accelerate, they should create waves in space-time, just as moving charges can create electromagnetic waves. But these gravitational waves would be incredibly faint by the time they reached Earth. Not faint like a quiet radio station. Faint in a way that makes the word faint look rather bold. A passing gravitational wave might change the length of a detector by less than the width of a proton. That is not the kind of thing you notice by looking out the window and saying, space-time seems a touch shorter today. To detect it, humanity had to build machines of almost absurd precision. Machines so sensitive that they could notice tiny changes in distance while the whole messy planet carried on rumbling, humming, shaking, and being generally unhelpful. Those machines were LIGO in the United States and Virgo in Europe. LIGO stands for Laser Interferometer Gravitational Wave Observatory, which is a very large name for a very delicate kind of listening. There are 2 LIGO detectors, one in Hanford, Washington, and one in Livingston, Louisiana. Each has long arms stretching out at right angles 4 kilometers in length. Laser beams travel down those arms, bounce between mirrors, and return. The idea is simple in outline and extremely difficult in practice. If a gravitational wave passes through Earth, it should stretch space slightly in one direction while squeezing it in another. That tiny change would alter the distance the laser beams travel. By comparing the beams, scientists can detect the faint signature of a wave. Of course, Earth is not a quiet place. Trucks drive by, winds blow, waves hit distant coastlines, small earthquakes ripple through the ground, equipment warms and cools. Birds, one assumes, continue with their own opinions. The detectors have to separate the whisper of space-time from all the ordinary noises of a planet that refuses to sit still. This is part of what makes the detection of gravitational waves so extraordinary. It is not just that the universe sent a signal, it is that humans built instruments quiet enough, clever enough, and patient enough to hear it. The first direct detection of gravitational waves was announced in 2016 from a signal recorded in 2015 when 2 black holes merged far away. That discovery was enormous. It confirmed a major prediction of general relativity and opened a new way of observing the universe. But black holes, as dramatic as they are, do not usually give us light when they merge. They are dark objects joining in darkness, leaving behind a gravitational signal, but no bright flash for telescopes to chase. With GW 170817, something different happened. The universe did not send only one kind of message. It sent a gravitational wave, and then it sent light. On August 17, 2017, the gravitational wave detectors noticed a long rising signal. It was not the brief heavy thump of 2 black holes merging. It lasted much longer, around 100 seconds, sweeping upward in frequency as the 2 objects spiraled closer and closer. Scientists call this kind of signal a chirp, which is a charmingly small word for the death spiral of 2 ultra-dense stars. It rose in pitch and pace, not through air, but in the data, a curve on a screen, a pattern in the noise, a message shaped by gravity. Then, less than 2 seconds later, a gamma ray burst was detected by space telescopes. Gamma rays are the most energetic form of light, and this short burst was another clue. Something powerful had happened. Something compact, fast, violent, and far away. The gravitational wave had told astronomers that two neutron stars had merged. The gamma rays suggested that the merger had launched a burst of high-energy radiation. Together, they were like two witnesses describing the same event from different sides of the room. One spoke in gravity, one spoke in light, and for the first time, astronomers could put those messages together. This is why GW 170817 matters so deeply. It was not simply another detection. It was the beginning of what scientists call multi-messenger astronomy with gravitational waves. Astronomy had always relied mostly on light, though light comes in many forms: visible light, radio waves, infrared, ultraviolet, X-rays, gamma rays. We built telescopes to catch each kind, because each one tells a different part of the story. Radio waves can show cold gas and magnetic fields. Infrared light can peer through dust. X-rays can reveal hot, violent regions around compact objects. But gravitational waves are not light at all. They're a different messenger, carrying information from the motion of mass itself. Imagine trying to understand a distant storm by watching flashes of lightning but never hearing thunder, or hearing thunder but never seeing where the lightning struck. For a long time, we had the light. Then gravitational wave astronomy gave us the thunder. GW 170817 gave us both from the same storm. It let astronomers hear the space-time ripple and then turn telescopes toward the fading glow. It was as if the universe had finally provided subtitles for one of its most dramatic scenes. The location was traced to NGC 4993, a galaxy about 130 million light-years away. That number is both enormous and, by cosmic standards, almost nearby. The light began travelling toward us when dinosaurs were still walking on Earth. While continents shifted, seas opened and closed, mammals changed, forests grew and vanished, and eventually humans appeared, learned to use fire, built cities, invented clocks, argued about clocks, and finally built gravitational wave detectors. The signal kept moving. It crossed intergalactic space with no hurry and no pause. By the time it reached Earth, there were scientists ready with lasers, mirrors, satellites, computers, telescopes, and probably a considerable amount of coffee. There is something quietly moving about that timing. The collision happened long before anyone could have known to wait for it, yet the signal arrived after humanity had developed the right tools to notice it. A little earlier, and it would have passed through Earth unheard. A century earlier, and it would have stretched and squeezed the planet by an amount too small for anyone to detect, then continued outward into space, leaving no entry in our records. But in 2017, the detectors were operating. The alerts went out. Observatories around the world turned toward the source. A small point of light was found near the galaxy. It brightened, changed colour, and faded in a way that matched what scientists expected from a kilonova, the glow from neutron-rich material thrown out by the merger. And that brings us to another reason this event became so famous. A neutron-star merger is not only loud in gravitational waves, it can also be a factory for heavy elements. Gold, platinum, uranium, and other heavy nuclei are not easily made in ordinary stars. Stars can fuse lighter elements into heavier ones up to a point, but building many of the heaviest elements requires extreme conditions, with lots of neutrons available very quickly. For years, scientists suspected that neutron star mergers could be one of the places where these elements form. GW 170817 gave powerful evidence that this was true. In the expanding debris of that collision, the universe was forging heavy elements and scattering them into space. So in a very real sense, that distant crash may have been the kind of event that helps explain why precious metals exist at all. The gold in a ring, the platinum in a laboratory instrument, the heavy elements inside Earth's crust. They may trace part of their ancestry to ancient collisions between neutron stars. Not necessarily this exact one, of course. We should not point at a necklace and confidently say, "Ah yes, NGC 4993. Very fashionable this season." But events like GW 170817 show us a process by which the universe makes some of its rarest ingredients. A violent merger becomes, over long enough time, part of planets, rocks, oceans, tools, and perhaps someone quietly twisting a ring on their finger while listening to a story about space. That is one of the gentle surprises of astronomy. The farther away we look, the more personal the universe becomes. At first, neutron stars seem remote, exotic, almost unreal. They are not part of ordinary life. You do not pass one on the way to the shop. You do not accidentally leave one in the laundry. But the elements made in such events can become part of worlds. The physics of dead stars becomes connected to the chemistry of living planets. A collision in a distant galaxy becomes part of the long explanation for why matter around us has the richness it does. Still, before we get too far ahead, it helps to return to the listening itself. Because hearing the universe in gravitational waves changes the basic idea of astronomy. For centuries, astronomy was what humans could see. Ancient people watched stars, planets, comets, eclipses, and the moon. Later, telescopes gathered more light than eyes could. Then cameras, spectrographs, radio dishes, space observatories, and high-energy detectors expanded our senses. We learned that the universe is not just what appears in the night sky. It glows in wavelengths our eyes cannot see. It hums with signals our bodies cannot feel. It carries stories in particles, radiation, and now in the shape of spacetime itself. GW 170817 was a reminder that the universe is not silent just because human ears are not built to hear it. Space is often called silent because sound, the kind we know, needs air or some other medium to travel through. In the vacuum between stars, there is no ordinary sound carrying voices or thunder or music. But gravity has its own way of carrying news. Space-time can ripple. Those ripples can cross vast distances, and with the right instruments we can translate them into signals, into graphs, into frequencies, into something we describe as a chirp. It is not sound in the everyday sense, but it can be made audible. Scientists can shift the signal into the range of human hearing, and suddenly a merger far across the cosmos becomes a rising tone. A tiny whoop from deep time. The universe, for a fraction of a moment, becomes something we can listen to. There is a soft irony in that. We spent thousands of years looking up, and then one of the great discoveries of modern astronomy arrived as something closer to listening. Not with ears, but with lasers. Not through air, but through space-time. Not a roar, but a measurement so small that it almost feels impossible. The first time we heard this kind of event, it was not in a grand hall or under a dramatic sky. It arrived in data pipelines, detector logs, automated alerts, observatory schedules, and careful human analysis. The universe gave the performance. The scientists checked the cables. That is the practical side of wonder, and I think it is worth appreciating. Big discoveries often sound majestic when told afterward. A new era began. A cosmic mystery was solved. A signal crossed the universe. All true. But inside the moment itself are people at desks, instruments needing calibration, emails arriving, software sorting patterns, telescopes waiting for darkness, and researchers trying to decide whether a faint dot near a distant galaxy is the thing everyone hopes it is. Science is not only revelation, it is also procedure. It is patience, caution, checking, rechecking, and refusing to let excitement outrun evidence. Even when the universe does something spectacular, someone still has to make sure it was not a glitch, and that caution made GW 170817 stronger, not weaker. Many instruments saw pieces of the event. LIGO and Virgo detected the gravitational wave. Space telescopes detected the gamma ray burst. Optical telescopes found the fading glow. Other observatories followed in ultraviolet, infrared, radio and X-rays. Each messenger added detail. The gravitational waves revealed the inspiral of compact objects. Their light showed the aftermath. The changing colours helped scientists understand the expanding debris. The delayed emissions helped reveal the outflow and jet. Instead of one clue, astronomers had a whole set of clues arriving in order, like a cosmic detective story, where the evidence was scattered across the electromagnetic spectrum. For a sleepy science story, this may sound almost too exciting, so let us hold it gently. No need to rush through the discovery as if we are late for a meeting with a neutron star. The important thing for now is the feeling of the doorway opening. Before GW 170817, gravitational wave astronomy had already begun with black hole mergers. But after GW 170817, we knew that gravitational waves could guide telescopes to visible cosmic events. We could hear where something happened and then look. We could combine the motion of space-time with the glow of matter. We could study the same event in two fundamentally different ways. That is why the phrase "when we heard the universe for the first time" has such a special meaning here. We had heard black holes before in the gravitational wave sense, but with GW 170817, we heard the universe and then saw it answer in light. We heard the deep gravitational note of two neutron stars spiraling together, and then we watched the ember of their collision fade. It was the first time humanity experienced such a complete message from this kind of event. Not complete in the sense that every mystery was solved. Science is rarely that tidy, and the universe is not known for providing answer keys. But complete in the sense that two messengers reached us together, each one confirming and enriching the other. As you rest there, perhaps with your breathing a little slower than when we began, picture the signal moving through the Earth. It did not stop at the surface. Gravitational waves pass through planets almost as if the planets are not there. The ripple moved through buildings, mountains, oceans, trees, sleeping animals, traffic, quiet bedrooms, and people who had no idea that space-time itself was briefly stretching and squeezing around them. Nothing dramatic happened in daily life. No lamps swung wildly, no clocks jumped from the wall. The effect was far too tiny for our senses. But inside those long detector arms, the lasers noticed. There is something comforting in that, oddly enough. The universe can be enormous, violent and strange, but our way of meeting it can be careful and quiet. We do not need to be huge to learn about huge things. We do not need to be loud to detect a whisper. On a small rocky planet, around an ordinary star in one galaxy among many, we built a pair of listening machines and waited. And when a message arrived from two dead stars in another galaxy, we understood enough to say, "This is real, this is distant, this is gravity carrying news." Tonight's journey begins there, at the edge between silence and signal. Ahead of us is the long path that made this moment possible. We will need to wander back to Einstein, to the idea that space and time are not separate pieces of furniture in the cosmic room, but part of one flexible structure. We will need to understand why moving masses make ripples, why those ripples are so hard to detect, and why two neutron stars are among the best drummers space-time could ask for, though admittedly not the sort of drummers you would invite into a small apartment. We will meet the detectors that listened, the telescopes that turned, and the fading kilonova that helped reveal where heavy elements are born. For now, just stay with the simple wonder of it. A long time ago, two neutron stars circled closer and closer. Their final moments shook space-time. That shaking crossed 130 million light-years. It reached Earth on a summer day in 2017. And for the first time, we were ready not only to see the universe, but to hear one of its deepest messages arrive. Long before humans built machines that could listen to space-time, gravity seemed like the most familiar mystery in the world. It was there every time a stone fell, every time rain tapped against the ground, every time a tired person looked at a staircase and quietly negotiated with physics. gravity was ordinary enough to be ignored and strange enough to shape the entire universe. It held the moon near Earth, Earth near the sun, and the sun inside the great turning city of the Milky Way. It guided tides, bent orbits, gathered dust into planets, and made sure that if you dropped a biscuit it would choose the floor with impressive confidence. For most of history, gravity was known by what it did, not by what it was. It pulled, it gathered, it kept things from wandering off into the dark, but no one knew, not really, whether gravity could also carry a message. At first, gravity felt like a silent command. Something happens here, and something over there responds. A fruit falls from a branch. A planet curves around the sun. A comet returns from the outer cold on a long-stretched path. The motions could be measured, predicted, written down and trusted. That was already remarkable. Ancient sky watchers did not need modern equations to notice that the heavens moved with rhythm. They watched the moon swell and shrink, watched bright planets wander against the fixed stars, watched eclipses arrive with a kind of terrifying precision. The sky was not random. It had rules. It had timing. It had a patience that human beings found both useful and slightly humbling. Then came Isaac Newton, who gave gravity a mathematical voice. In his picture, every mass attracted every other mass. The Earth pulled on an apple. The apple pulled on the Earth too, though the Earth, being rather larger and less easily impressed, did not leap upward in response. The sun pulled on the planets, and the planets pulled on the sun. Gravity acted between objects across distance, and Newton's equations could describe that attraction with astonishing success. Suddenly the same idea explained falling objects and orbiting worlds. The apple and the moon became part of the same story, which is a beautiful thing, even if the apple has received far more publicity than most pieces of fruit can reasonably expect. Newton's gravity was powerful, elegant, and wonderfully practical. It helped scientists predict planetary motion, understand tides, and guide navigation. It gave the universe a clockwork feeling. If you knew where things were and how fast they moved, you could calculate where they would be later. This was gravity as a kind of invisible architecture, a set of rules connecting mass to motion. And for many everyday purposes, Newton's gravity still works beautifully. It will help you launch a ball, design a bridge, and understand why your tea stays in the cup instead of floating toward the ceiling, which is considerate of it. But Newton's gravity also carried a strange implication. It seemed to act instantly. If the sun somehow vanished according to the simple Newtonian picture, Earth would immediately know. It would stop orbiting and head off along a straight path into space, presumably with all of us having a very bad morning. This instant action at a distance bothered even Newton. He could describe gravity with precision, but the deeper mechanism remained unclear. How did one object reach across empty space and influence another? What was carrying the instruction? Was there some hidden rope, some invisible pressure, some field, some medium, some quiet cosmic bookkeeping system, making sure that every mass knew where every other mass was? The answer had to wait. Science often works that way. One generation builds a bridge halfway across a foggy valley, and another generation much later sees where it was leading. Newton's laws were not wrong in the way a bad guess is wrong. They were incomplete in the way a map of one town is incomplete if you're trying to understand a continent. They were accurate where speeds were slow, gravity was moderate, and the universe behaved politely. But when light, speed, space, and time entered the discussion, the old picture began to strain. Albert Einstein changed the question. Instead of asking how gravity pulls across space, he asked what gravity says about space itself. In 1915, with general relativity, gravity stopped being a simple force tugging between objects and became the shape of space-time. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. This is one of those sentences that sounds calm enough until you really sit with it. Space and time are not a fixed empty stage where the universe performs. They are part of the performance. They can bend, they can stretch, they can respond. A common image is a heavy ball resting on a soft rubber sheet. The sheet curves around the ball and smaller balls roll along curved paths nearby. This gives a helpful first impression, though it is also a little sneaky, because the rubber sheet is being pulled down by gravity while trying to explain gravity, which is rather like using a kettle to explain why kettles exist. Still, as a bedtime doorway into the idea, it works well enough. The sun curves the space-time around it. Earth follows a path through that curved space-time. Earth is not being yanked by a mysterious hand across emptiness. It is moving along the natural path available to it in a curved geometry. Now, if space-time can curve, then space-time can also change. And if it can change, then those changes should not happen everywhere instantly. Einstein's universe has a speed limit, the speed of light. No signal, no influence, no meaningful message can travel faster than that. So if the sun could vanish, which it cannot do politely, and will not be doing during this video, Earth would not know immediately. For about 8 minutes our planet would continue along as if nothing had happened, because that is how long light and gravity's changing influence would take to cross the distance from the sun to us. Gravity, in Einstein's view, does not issue instant commands. It sends updates through space-time at a finite speed. That is where the idea of gravitational waves begins to appear. If a massive object changes its motion in the right way, it can disturb the curvature of space-time, and that disturbance can travel outward. Not every movement produces a strong wave. You waving your hand gently in bed technically changes the gravitational field around you, but the effect is so tiny that the universe does not pause to take notes. For gravitational waves strong enough to detect across cosmic distances, you need enormous masses moving violently, black holes orbiting each other, neutron stars spiraling together, stellar cores collapsing, things that make ordinary ideas of motion seem like a sleepy shuffle across a carpet. A gravitational wave is not a wave in air. It is not sound, not pressure, not a ripple in some hidden cosmic ocean. It is a ripple in the distances themselves. As it passes, it stretches space in one direction and squeezes it in another, then reverses the pattern again and again. If one passed through your room, the distance from wall to wall would change by an unbelievably tiny amount. You would not feel it. Your lamp would not tremble. Your pillow would not rise dramatically and whisper, "Did you notice that?" The effect is far too small, but in principle, space itself has shifted ever so slightly. The ruler has changed along with the thing being measured, which is exactly the sort of idea that makes physics both beautiful and mildly rude. Einstein predicted gravitational waves, but for a long time they remained almost ghostly. The mathematics allowed them. The theory seemed to require them, but could they ever be measured? Even Einstein wondered whether they were too faint to detect or whether they were mathematical artifacts rather than physical realities. This uncertainty lasted for decades. Scientists debated what the waves meant, how much energy they carried, and whether they could be observed in practice. General relativity had already explained many things, including the odd precession of Mercury's orbit and the bending of starlight near the sun. But gravitational waves were harder. They were messages so faint that even knowing they existed did not mean we had any way to read them. Then astronomy found a clue in a place that already sounds like a science fiction instrument, a binary pulsar. A pulsar is a rotating neutron star that beams radiation from its magnetic poles. If those beams sweep across Earth, we see pulses, regular flashes like the ticks of a cosmic lighthouse. Pulsars can be extraordinarily precise. Some are so steady that their pulses can rival the regularity of atomic clocks. So when a pulsar is part of a pair, orbiting with another compact object, its timing becomes a way to study gravity in extreme conditions. In the 1970s, Russell Hulse and Joseph Taylor discovered a pulsar in a binary system. By carefully measuring the arrival times of its pulses, they could track how the orbit changed. The two objects were slowly spiraling closer together. They were losing energy. The amount of energy lost matched what general relativity predicted would be carried away by gravitational waves. This was not a direct detection. No instrument on Earth had felt the ripple pass through, but it was strong indirect evidence. It was as if scientists could not yet hear the song, but they could see the dancers slowing down exactly as if music were carrying energy away. That binary pulsar was a major step toward believing that gravity could send a real physical message. It showed that gravitational waves were not just elegant mathematics sitting quietly in an equation. They seemed to affect the motion of real stars. Something was leaving the system. Something was carrying energy into space. The universe had begun to hint that it could speak through gravity, though humanity still did not have the right ears. Building those ears became one of the most ambitious experimental challenges in modern science. To hear gravitational waves directly, scientists needed to measure changes in distance smaller than anything normal life prepares us to imagine. The passing wave would not move a mirror by a visible amount. It would change the length of a detector arm by a fraction of the width of a proton. Try picturing that gently, without letting it bother your sleep too much. A proton is already far smaller than an atom. Now imagine measuring a fraction of that change over kilometers of distance, while the ground beneath your instrument shakes from distant ocean waves, passing vehicles, weather, tiny seismic tremors, and all the other small restlessness of Earth. The solution was a laser interferometer. The basic idea has a lovely simplicity. Send laser light down two long arms set at right angles. Let the beams bounce between mirrors and return. If the arms are exactly the same effective length, the light waves combine in a predictable way. But if a gravitational wave passes through, it stretches one arm and squeezes the other by a tiny amount. That changes how the light waves line up when they return. The pattern shifts. The detector notices. In practice, of course, nothing about this is simple. The mirrors must be isolated from vibration. The lasers must be extraordinarily stable. The vacuum tubes must be huge and clean. The data analysis must separate genuine signals from noise. The whole instrument has to behave as if it is resting in a calm universe, while located on a planet that is very much not calm. This is the part of the story where patience becomes heroic. For years, detectors listened and heard nothing confirmed. Not because the idea was foolish, but because the signals were rare, faint, and difficult. Science at this scale can look from the outside like waiting, but it is a very active kind of waiting. Engineers improve mirrors, physicists refine models, data analysts study noise, teams check and recheck, instruments are upgraded, sensitivity improves, the silence narrows. The universe is not refusing to speak. We are learning how to hear. There is something deeply human about that. A gravitational wave passing through Earth is not dramatic to the senses. It does not announce itself with thunder. It does not paint the sky green or knock over garden chairs. It asks to be noticed through care. Humanity had to build a quiet place inside the noise of the world. Two long arms stretching across land, lasers moving in vacuum, mirrors suspended with exquisite precision, computers waiting for patterns. The listening was not done with ears, but it still had the emotional shape of listening. Be still. Be careful. Do not decide too soon. Let the faint thing become clear. When the first direct gravitational wave detection happened in 2015, it came from two black holes merging more than 1 billion light-years away. The signal was brief and beautiful in the data, a rising chirp that matched the prediction of general relativity. Two black holes, invisible by their nature, had spiraled together and joined. For a fraction of a second, the power emitted in gravitational waves was enormous, yet by the time those waves reached Earth, they were almost unimaginably weak. LIGO detected them anyway. A A century after Einstein's theory, space-time had finally been heard directly. That detection changed astronomy. Until then, almost everything we knew about the distant universe came through light or particles. Light is generous. It gives us images of galaxies, spectra of stars, radio maps of gas, X-ray views of hot matter near black holes. But light can also be blocked, scattered, absorbed, or never emitted in the first place. Black holes merging in darkness do not offer much visible light for telescopes to collect. Gravitational waves, though, pass through matter almost without caring. They can escape from places where light struggles. They carry information from the motion of dense objects themselves. They do not show us the surface of an event. They tell us about the movement of mass deep in the heart of it. In a way, this gave the universe a new sense. We'd been watching the cosmos for thousands of years. Now we could listen to its heaviest motions. Not listen as we listen to rain, or music, or someone talking softly in the next room. Listen by translating spacetime's tiny stretch into data, and data into a signal, and the signal into something human beings can understand. The sound is not literal, but it is meaningful. When scientists turn a gravitational wave into an audible chirp, they are not inventing the event. They are shifting its frequencies into the range our ears can notice, the way a telescope shifts invisible light into colours we can see. It is a translation, and like many translations, it carries both precision and wonder. Still, the first detections from black holes were mostly heard and not seen. They opened the door, but the room beyond was dark. That darkness was not disappointing. Black holes are supposed to be dark. Their mergers were perfect gravitational wave events, massive, compact, fast, clean. But astronomers hoped for something more. What if a gravitational wave could arrive from an event that also made light? What if the detectors could send an alert, telescopes could turn, and the same cosmic event could be studied in two different languages? Gravity and light together, motion and glow. The deep structure of space-time and the hot debris of matter. For that, neutron stars were ideal. Unlike black holes, neutron stars have surfaces, or at least something surface-like in the extreme sense. They are made of matter compressed beyond ordinary understanding. When two neutron stars merge, they do not simply vanish into darkness, at least not immediately. They can tear material away. They can launch jets. They can produce gamma rays. They can heat neutron-rich debris until it glows. They can make a kilonova, a fading fire rich with newly formed heavy elements. If black hole mergers are like hearing a door close in a dark house, neutron star mergers are more like hearing the door and then seeing a flash under it. This possibility had been imagined and modelled for years. Short gamma-ray bursts, brief flashes of high-energy light, were suspected to come from neutron star mergers. Heavy elements were thought to form in the debris from such collisions. Gravitational waves from neutron star inspirals had a predicted shape, longer and more detailed than the signals from heavy black holes. The theory was waiting for the event. The instruments were waiting too. Astronomers had prepared networks, alerts, follow-up plans, telescope time, and software tools. They knew that if such a signal came, they would need to move quickly, because the light would fade. The universe might speak in gravity first, but the glow would not wait around forever while everyone found their keys. This is where the phrase "before the sound" becomes more than a poetic idea. Before humanity heard GW 170817, gravity had spent a century becoming understandable as a messenger. First, it was a force in Newton's equations. Then it became curvature in Einstein's theory. Then it became a wave that could carry energy. Then binary pulsars gave indirect evidence that such energy was truly being carried away. Then detectors were built to feel the faintest stretching of space. Then black holes proved that direct detection was possible. Each step taught gravity how to speak to us, or perhaps more accurately, taught us how to stop misunderstanding its silence. Because gravity had always been carrying messages. The falling apple carried a message about Earth. The Moon's orbit carried a message about mass and motion. Mercury's strange orbit carried a message about curved space-time. The binary pulsar carried a message about energy leaving through gravitational waves. What changed was not gravity's willingness to communicate. What changed was our ability to read the messages. The universe had been writing in a language older than stars, and we had slowly been learning the alphabet. It is worth pausing on how gentle the message becomes by the time it reaches us. Near the source, a pair of compact objects can churn space-time violently. Close to merging neutron stars, gravity is fierce, rapid, and extreme. Space-time is not politely curved there. It is dragged and stirred by masses moving at a significant fraction of the speed of light. But as the waves spread outward, they weaken. By the time they cross Earth, they are soft beyond softness. They pass through our planet, our bodies, our rooms, and our instruments. Only the instruments notice, and only because they were built to be almost impossibly sensitive. That softness does not make the event small. It makes the detection profound. There is a quiet lesson in it. Not all powerful things arrive loudly. Some of the greatest messages in science come as tiny deviations, slight shifts, faint pulses, small mismatches between what was expected and what occurred. A star appears to wobble. A spectrum has an extra line. A clock ticks a little differently. A laser beam returns a little out of step. The universe often reveals itself not by overturning the table, but by moving one grain of dust and waiting to see whether anyone notices. So, before we arrive at the neutron stars of GW 170817, before the gamma-ray flash, before the telescopes turn toward NGC 4993, there is this older story of gravity becoming a messenger. It begins with falling objects and orbiting moons. It passes through Newton's law and Einstein's curved space-time. It moves through decades of argument, calculation, indirect evidence, experimental patience, and machines built on a scale that would have seemed absurd to earlier generations. And all of it leads toward one particular morning in August 2017, when the detectors did not just hear a short dark chirp from black holes, but a longer signal, a rising sweep, the final inward spiral of two neutron stars. The sound had been travelling long before we were ready for it. The message had crossed intergalactic space while Earth lived through ages of change. It had no idea, if a wave can be said to have ideas, that a young technological species had finally learned how to listen. It simply moved outward at the speed of light, carrying the story of mass in motion. By the time the signal we call GW 170817 reached Earth, the event itself was already ancient history. The two stars had already met, collided, torn at each other, and changed into something new long before any human instrument noticed the faint message they had sent. But to understand what that message meant, we have to move our attention away from the detectors for a while and drift back toward the source, to a galaxy far beyond the Milky Way, where two of the strangest stars in nature were locked in one of the tightest dances the universe can make. They were neutron stars, and that simple phrase contains so much compressed physics that it almost deserves to be said carefully, like lifting something very heavy with both hands. A neutron star is what can remain after a massive star dies. Not every star ends this way. Our Sun, for instance, is not massive enough. It will one day become a white dwarf, a dense glowing ember, which is dramatic enough for a family star, but not quite the extreme end of the menu. A more massive star can burn through its nuclear fuel, build heavier and heavier elements in its core, and eventually reach a point where it can no longer support itself against gravity. The core collapses. The outer layers explode outward in a supernova. For a brief time, one star can shine with the power of billions, and in the centre, if the mass is just right, not small enough to become a white dwarf, and not quite large enough to collapse all the way into a black hole, the crushed remnant becomes a neutron star. The name is not decorative. In a neutron star, matter has been squeezed so hard that protons and electrons are forced together, forming neutrons. the object becomes something like an enormous atomic nucleus, though enormous here means about the size of a city, while still holding more mass than the Sun. It is a wonderful example of the universe using the word small in a deeply unfair way. Across perhaps 20 kilometers or so, a neutron star can contain a mass greater than our entire star. The gravity at its surface is overwhelming. The magnetic fields can be intense. The density is almost beyond ordinary imagination. If you tried to build a mental model from familiar objects, you would quickly run out of furniture, mountains, and sensible comparisons. Still, let us try gently. Imagine the Sun, not its light, not its warmth on your face, but its mass. All that material, enough to hold the planets in orbit, enough to dominate the solar system. Now compress more than that into a sphere small enough that you could drive across it in a short time. Assuming you had a car that could survive impossible gravity, which you do not, and assuming the local traffic laws had survived stellar collapse, which seems unlikely. That is the sort of object involved in GW 170817, and there were two of them. How do two neutron stars end up together? The answer begins with two ordinary massive stars born as a pair. Many stars are not alone. They form in binaries, orbiting a shared centre of mass, growing old together in a relationship that can become, by human standards, somewhat intense. The more massive star evolves first. It swells, sheds material, may transfer gas to its companion, and eventually explodes as a supernova, leaving behind a neutron star. If the system survives that explosion, which is not guaranteed, the second star continues evolving. Later, it too dies in a supernova, and if the binary is still bound after all that violence, the result can be two neutron stars orbiting each other. That already sounds like a miracle of survival. Two stars are born together, both live short, brilliant lives, both explode, and somehow the remaining dense cores are still gravitationally linked. The system has been kicked, stripped, shaken, and remade, yet the pair remains. They're no longer shining stars in the normal sense. They are compact remnants, dead cores with enormous gravity circling in the dark. They may continue that way for millions or billions of years, slowly losing orbital energy through gravitational waves. Each orbit sends out a little ripple in spacetime. Each ripple carries away energy. The orbit shrinks, the stars move closer. It is not quick at first. The tightening can be very slow, like a clock winding down over cosmic time, except the clock is made of collapsed stellar cores and the ticking is gravity itself. This is the long beginning of GW 170817. Not the final collision, but the patient inward spiral. For ages the two neutron stars orbited each other. Their paths were not static. They were slowly falling together, though falling in orbit is always a little strange to picture. They were not dropping straight inward. They were moving around each other, around and around, while the orbit gradually tightened. It is a little like water circling a drain, though that image is too gentle and far too wet. The important part is that the motion was speeding up. As the stars came closer, they orbited faster. As they orbited faster, they emitted stronger gravitational waves. As they emitted stronger waves, they lost energy more quickly. The process fed on itself, quiet for most of its life and then suddenly urgent near the end. This is what scientists call an inspiral. The word is exactly what it sounds like, a spiral inward. For gravitational wave detectors, the inspiral is especially valuable because it leaves a pattern. The wave frequency rises, the amplitude grows, the signal sweeps upward in a shape often called a chirp. If you listen to the translated data, it is a small rising sound, almost modest, considering the violence that made it. The chirp carries information. It tells scientists about the masses of the objects, how fast they were moving, how the orbit was shrinking, and whether the objects were likely black holes or neutron stars. In the case of GW 170817, the signal lasted long enough in the detector band to reveal a great deal. It was not just a brief thump. It was a long, rising gravitational note from two compact bodies circling closer and closer. About 100 seconds before the merger, the neutron stars were still separated by hundreds of kilometers. That sounds close on cosmic scales, but for objects only about city-sized, it was still enough room for the final approach to unfold in the data. They were orbiting many times each second. Take a moment with that, because it is easy to let the number pass by too casually. These were objects heavier than the Sun, each one an ultra-dense remnant of a dead star, and they were whipping around each other faster than the blades of a kitchen mixer. A kitchen mixer, to be clear, is not usually made of nuclear density matter, which is best for everyone involved. With every orbit, spacetime rippled. With every ripple, the stars gave away a little more of their orbital energy. With every loss, they came closer. In the final seconds, the process became extreme. The stars were moving at a significant fraction of the speed of light. Their gravitational fields were tearing at each other. Each star raised tides on the other, but these were not tides like the ocean bulging under the moon. These were distortions in ultra-dense matter, the stars stretching under mutual gravity. The way a neutron star deforms in those last moments tells scientists something about what it is made of, or more carefully, about the equation of state of neutron star matter. That phrase sounds rather dry, like something printed on a laboratory folder, but it points to one of the deepest questions in nuclear physics. How does matter behave when it is compressed beyond the density of an atomic nucleus? Is it stiff? Is it soft? Does it contain exotic particles? Does it change into forms we have never observed on Earth? We cannot scoop material out of a neutron star and study it in a laboratory, which is probably for the best. So instead, we look at how neutron stars behave when gravity pushes them to their limits. A merger, like GW 170817, is not only an astronomical event, it is also a physics experiment too large to fit inside any building. The final gravitational waves carry clues about how much the stars were distorted before they touched. A more easily deformed star leaves a slightly different imprint than a more compact, resistant one. Scientists have to extract that information carefully because the signal is faint, the models are complex, and the last moments are difficult to describe. But the possibility is extraordinary. By listening to a ripple from another galaxy, we can learn about matter in a state impossible to recreate on Earth. Now, what does it mean for two neutron stars to touch? This is not like two billiard balls clicking together. Neutron stars are not solid balls in the familiar sense, with clean surfaces and neat edges. They're layered, extreme magnetic relativistic objects. Their outer crust may be made of exotic nuclear structures, sometimes given whimsical names like nuclear pasta, because even physicists, when faced with the strangest matter in the universe, apparently get hungry. Beneath the crust, the material becomes denser and stranger. The boundary between one neutron star and another during a merger is not a polite collision between tidy objects. It is a violent blending, tearing, heating, and compression of matter under gravity so strong that space-time itself is severely curved. As the stars reach the end of the inspiral, tidal forces can strip material away. Some matter is thrown outward in tails, some is squeezed and shocked, some falls inward. Some may form a hot disk around the central remnant. The collision can launch jets from near the poles, depending on the remnant and magnetic fields. It can eject neutron-rich debris into space, where heavy elements begin forming through rapid neutron capture. But we're moving slightly ahead of ourselves now, because the light, the kilonova, and the heavy elements deserve their own careful rest later in the journey. For the moment, it is enough to understand that GW 170817 was not a simple crash. It was the final stage of a long binary life, a transformation of two dead stars into a new compact object, and a cloud of glowing, element-making debris. One of the great questions after a neutron-star merger is what remains at the centre. Does the merged object collapse almost immediately into a black hole? Does it briefly become a hypermassive neutron star, supported for a short time by rapid rotation and heat before collapsing? Does it survive longer as a massive neutron star? For GW 170817, scientists have debated the details using gravitational waves, gamma rays, X-rays, optical and infrared light, and theoretical models. The total mass inferred for the system was heavy enough that a black hole likely formed at some stage, but the exact timing and intermediate state are part of the continuing investigation. This uncertainty is not a flaw in the story. It is the story doing what good science stories do. It gives us something real, and then it gives us better questions. The gravitational wave signal itself mostly told us about the inspiral, the time before the stars fully merged. That is because the detectors were most sensitive to the rising wave from the orbital motion. The moment of merger and the immediate aftermath were more difficult to read directly in gravitational waves for this event. But the inspiral was enough to identify the source as a binary neutron star. The masses were in the range expected for neutron stars. The signal lasted much longer than the earlier black hole merger signals, and the later light confirmed that this was not a pair of black holes disappearing into darkness. It was matter, real dense matter, colliding and shining. There is a difference in feeling between black hole mergers and neutron star mergers. Black holes are clean in a certain mathematical way. They have mass, spin, and charge, though astrophysical black holes are usually described mainly by mass and spin. When two black holes merge, the result is mostly a larger black hole and gravitational waves. There may be no ordinary matter nearby to glow. It is gravity speaking almost alone. Neutron stars, on the other hand, bring matter into the drama. They have interiors, crusts, magnetic fields, possible atmospheres, temperatures, and nuclear physics. When they merge, gravity is still the conductor, but matter joins the orchestra, and matter is messy in the most useful way. It glows, it ejects, it changes, it forms elements, it gives telescopes something to chase. That is why GW 170817 became so important. It was not merely that two compact objects merged. It was that the merging objects were neutron stars, which meant the event could connect many fields at once. General relativity, nuclear physics, high-energy astrophysics, gamma-ray bursts, heavy element formation, cosmic distance measurements, and the life cycles of stars all met in one signal. A pair of objects only city-sized, located in a galaxy about 130 million light-years away, managed to bring together half the astronomy department, so to speak, and several departments next door. Not bad for two dead stars that had no interest in attending a conference. If you picture the final orbit, do not imagine a wide, graceful dance. By the end, the neutron stars were moving too fast and too close for anything gentle. Their orbital frequency rose rapidly. The gravitational waves grew stronger and higher in frequency. The space between them shrank until the objects could no longer remain separate. Their surfaces, or outer layers, met and tore. The combined mass churned. For a brief time, the remnant may have been a distorted, rapidly spinning object, hot and unstable. Around it, matter formed an accretion disk. Outflows began, debris expanded. The conditions became right for the making of heavy elements, and from near that chaos a short burst of gamma rays escaped, reaching Earth just after the gravitational wave. The timing is worth holding in mind because it gives the event a kind of sequence. First came the gravitational wave carrying the story of the inspiral. Then came the gamma rays, a brief flash of high-energy light. Then came the optical and infrared glow of the kilonova, fading over days as the debris expanded and cooled. Later came radio and X-ray emission, revealing more about the outflow and its interaction with surrounding material. The event did not happen once in our observations. It unfolded. Different messengers arrived and changed over time, like different instruments entering after the main note. This is one reason scientists were able to learn so much. A single still image would not have been enough. A single chirp, would not have been enough. The changing pattern told the story. But at the heart of everything was the inspiral. 2 neutron stars, born from massive stars, surviving supernovae, orbiting for ages, losing energy through gravitational waves and finally merging. That is what GW170817 really was. The name sounds technical because it is a label, gravitational wave, year 2017, August 17th. Yet behind the label is a full cosmic biography. It tells of stellar birth, stellar death, binary survival, patient orbital decay, extreme matter, curved space-time, and a final collision that shook the universe just enough to reach a planet with listening machines. There is something almost tender about the long wait before the end. For millions or perhaps billions of years, the 2 neutron stars were bound together. They had no light like ordinary stars, no gentle warmth, no planets in any comfortable sense, no quiet sunrise. They simply circled, dense and dark, carrying their history in their masses and motion. Their orbit was a clock, and the clock was running down. Not in a dramatic, visible way from moment to moment, but inevitably. Every gravitational wave they emitted was a little subtraction from the orbit. Every subtraction made the next orbit slightly tighter. The end was written not as fate in a mystical sense, but as physics. Given enough time, the stars would meet, and when they did, the meeting lasted almost no time at all, compared with the long spiral that preceded it. This contrast is common in the universe. Long preparation, sudden change. A star spends millions of years burning, then collapses in seconds. A binary system in spirals for ages, then merges in a blink. A signal crosses space for 130 million years, then passes through a detector in minutes. Even on Earth we know this pattern in smaller ways. A storm gathers all afternoon, then breaks in a sudden rain. A kettle heats quietly, then begins to sing. A thought sits at the back of the mind for days, then becomes clear all at once. The universe often takes its time getting ready. What made GW170817 special was that we caught the ending from far away. We did not see the neutron stars themselves as little spheres. No telescope imaged them directly. They were far too small and distant. Instead, we inferred them from the message they sent. The gravitational wave was like listening to footsteps behind a wall and knowing the weight, speed and direction of the person walking there. Except in this case, the footsteps were ripples in space-time. The wall was 130 million light-years of universe, and the walkers were 2 collapsed stars orbiting each other 12 times a second. As comparisons go, it asks a bit of the imagination, but then astronomy usually does. A useful thing to remember is that the signal was not a recording of sound made at the source. Space has no air to carry ordinary sound from one galaxy to another. The neutron stars did not make a boom that travelled through emptiness. Instead, their motion changed the curvature of space-time. That changing curvature travelled outward as gravitational waves. When the waves passed through the detectors on Earth, scientists converted the pattern into audio frequencies humans could hear. The chirp we listen to is a translation, not a microphone recording, but it is faithful in the important sense. It preserves the rising frequency of the inspiral. It lets human ears experience a pattern made by gravity. That translation gives the event a special place in human feeling. Seeing is the old language of astronomy. We look up, we watch, we point telescopes. Listening feels different. Listening suggests closeness. Even when the source is impossibly far away, a sound reaches you. It enters your room, your body, your attention. Of course, GW170817 did not reach us as sound, but when we translate the signal, we give ourselves a way to experience what the detectors measured. The universe becomes, briefly, not only visible, but audible. And this particular audible trace came from 2 neutron stars whose last shared motion carried clues about gravity, matter, light, and the origin of heavy elements. So when someone asks what GW170817 really was, the simplest answer is that it was the merger of two neutron stars in a distant galaxy. But the fuller answer is softer and larger. It was the end of a binary system that had survived two stellar deaths. It was a 100-second gravitational wave signal from the final inspiral of ultra-dense matter. It was a test of Einstein's theory under extreme conditions. It was a glimpse into the behaviour of matter denser than atomic nuclei. It was the likely birth of a compact remnant, perhaps quickly becoming a black hole. It was the beginning of a flash, and a fading glow that telescopes around Earth would soon follow. It was a cosmic event with more than one voice. The wave did not arrive like a storm. It did not rattle windows, shake cities, or make anyone look up from breakfast with the sudden feeling that space itself had just moved. It passed through Earth with almost perfect politeness, slipping through oceans, continents, buildings, trees, people, and sleeping animals without leaving any ordinary sign behind. If you had been standing beside one of the detectors at the exact moment it arrived, you would not have felt a shiver under your feet. You would not have heard a note in the air. The birds, if there were birds nearby, would have continued their day with the calm confidence of creatures who are not responsible for interpreting general relativity. And yet, for a tiny fraction of human history, something extraordinary was happening. A ripple made by two neutron stars in another galaxy was stretching and squeezing the space around Earth by an amount so small that it almost sounds like a joke told by a very serious physicist. That is the strange beauty of GW170817. The event that created it was enormous, violent, and bright enough in its aftermath to occupy telescopes around the world. But the part that reached the gravitational wave detectors was delicate beyond imagination. By the time the ripple crossed 130 million light-years, it had spread so widely and weakened so deeply that Earth experienced it as an almost invisible tremble in distance itself. Not a tremble of matter in the usual sense, a tremble of measurement, a change in the spacing between things. For a moment one direction was stretched while another was squeezed, then the pattern reversed, and it did so in the quiet mathematical way that gravitational waves do. Nothing broke, nothing fell. The universe simply adjusted its geometry by a tiny amount and moved on. It helps to remember how long that signal had been travelling. The merger happened in a galaxy called NGC 4993, about 130 million light-years away. That means the message began its journey when Earth was a very different world. The continents were not arranged as they are now. The Atlantic was wider than it had once been, but the human story had not even begun. There were no telescopes, no clocks, no observatories, no little devices in pockets telling people they had missed 3 calls and needed to update software. The signal left its source while life on Earth was moving through deep biological time, through forests and seas and extinctions and recoveries, through the long, patient rearrangement of the planet. Then, while mammals evolved, while primates appeared, while early humans learned to shape tools, while languages formed and cities rose, the ripple kept travelling. It crossed space without hurrying, because travelling at the speed of light is already the universe's strictest kind of hurry. It did not slow down for galaxies. It did not stop to admire nebulae. It did not need a medium, a road, or permission. It was a change in space-time moving through space-time, carrying the final orbital rhythm of 2 dead stars. By the time it reached Earth, human beings had learned to predict eclipses, build observatories, discover gravity's laws, overturn those laws with deeper ones, split atoms, launch satellites, and argue about whether the office microwave should be cleaned by whoever used it last. A great deal had happened here. The wave had simply been on its way. Then, on August 17th, 2017, it arrived. To the universe, this was just the continuation of a journey. To us, it became an event with a date, a time, a label, and a place in scientific history. At 12:41:04, UTC, the signal passed through the network of gravitational wave detectors on Earth. The two LIGO detectors in the United States, one in Livingston, Louisiana, and one in Hanford, Washington, recorded it. Virgo, near Pisa in Italy, was also operating. The timing and strength of the signal at the different detectors helped scientists narrow down where in the sky the wave had come from. That detail matters more than it might sound at first. If you hear a sound with one ear, you know something happened, but not exactly where. If you hear it with two ears, your brain uses the slight timing difference to locate the source. A network of gravitational wave detectors works in a somewhat similar spirit, though with more lasers, more vacuum tubes, and fewer moments of wondering whether the noise was just the refrigerator. The signal from GW 170817 was different from the black hole mergers detected before it. Those earlier signals had been brief, quick chirps from heavy objects merging in darkness. GW 170817 lasted much longer in the sensitive band of the detectors, around 100 seconds. That length was one of the great clues. The two objects were lighter than the black holes previously observed by LIGO, so they spent more time circling through the range of frequencies the detectors could hear. Their final inspiral left a long rising track in the data. It began lower, then climbed higher as the stars orbited faster and faster. To scientists, this shape was not random. It was the pattern expected from two compact objects losing energy to gravitational waves as they spiraled inward. Imagine listening to a distant spinning coin as it rolls across a table. At first the sound is slow and separated, then faster, tighter, rising, until the coin finally settles with a little flutter. Now remove the table, remove the air, replace the coin with two neutron stars heavier than the sun, replace sound with ripples in space-time, and put the whole thing in another galaxy. The comparison is not perfect, but it carries the idea of a rising pace, a system moving toward an unavoidable end. GW 170817 was that rising pace written into gravity. The detector data held the record of the stars' last shared orbits, their motion becoming more urgent until the signal swept upward and faded into the merger. For a gravitational wave detector, the word tremble must be used carefully. The mirrors inside LIGO did not swing around visibly. The arms did not lengthen by anything a human could see. The change was smaller than the size of an atomic nucleus, smaller than everyday language is comfortable describing. LIGO's arms are 4 kilometers long, and the passing wave changed the relative length of those arms by only a tiny fraction of a proton's width. This is the kind of measurement that makes ordinary precision seem like measuring a room with a garden rake. Yet that is what the instruments were built to do. They were designed to notice when the distance travelled by laser light changed by an almost impossible amount. The detectors do this with laser interferometry, a phrase that sounds technical because it is, but the basic idea can be held gently. A laser beam is split and sent down 2 long arms at right angles. The beams reflect from mirrors and return. When they come back together, their light waves combine. If the arms stay the same length, the pattern remains steady. If a gravitational wave passes through, it stretches one arm and squeezes the other, changing the distance the light travels. That change shifts the pattern. The detector sees the difference. In a sense, the machine is asking the universe the same question over and over again. Are these two distances still exactly as they were? Most of the time, the answer is buried in noise. On August 17th, 2017, hidden in the noise came a very particular answer. Of course, the detectors do not simply declare "aha," neutron stars, and make everyone tea. The real process is careful. The instruments collect data continuously. Software searches for patterns that match predicted gravitational wave signals. Scientists compare results from multiple detectors. They check whether the signal might have been caused by local disturbances, equipment behavior, or some other earthly nuisance. They estimate the masses of the objects, the distance to the source, the position on the sky, and the confidence that the signal is astrophysical. This is science at its most patient, even when the discovery itself is exciting. The universe may offer a clue quickly, but humans still have to treat it with respect. GW 170817 had an extra twist. One of the LIGO detectors, the Livingston detector, recorded the signal strongly. Hanford also recorded it, though there was a brief instrumental glitch near the time of the event that had to be carefully removed from the data. Virgo's detection was weaker, which was not a failure. In fact, Virgo's relative lack of a strong signal helped localization. Because gravitational wave detectors have directional sensitivity, a weak signal in one detector can tell scientists that the source was in a part of the sky where that detector was less responsive. It is a bit like not hearing something clearly from one side of a room and using that absence as part of the clue. Even quietness can be informative if you understand the room. Together, LIGO and Virgo narrowed the search area enough for astronomers to begin the next part of the hunt. This was crucial because the sky is very large, and telescopes need to know where to look. A gravitational wave signal alone can often point to a broad region, not a neat little dot with an arrow saying, "Cosmic collision here." With GW 170817, the network provided a region of sky that telescopes could search. Then another messenger arrived almost immediately, gamma rays. About 1.7 seconds after the gravitational wave signal, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst. The European Integral satellite also saw it. That near coincidence was electrifying. Gravity had spoken, and high-energy light had answered. This delay of less than 2 seconds after 130 million years of travel is astonishing. The gravitational waves and gamma rays had crossed a vast distance, and they arrived at Earth almost together. That does not mean the gamma rays were necessarily emitted at the exact same instant as the gravitational waves from the merger. The physics near the source can introduce a delay. A jet may need time to form, break through surrounding material, or produce gamma rays. But the small difference in arrival time still showed that gravitational waves and light travel at nearly the same speed over cosmic distances. It was a beautiful test of fundamental physics, delivered not by a laboratory on Earth, but by 2 neutron stars that had ended their lives in another galaxy. Pause with that for a moment. Over 130 million years, a difference of only about 2 seconds appeared between the gravitational signal and the gamma ray signal. If you and a friend began walking from one side of a country to the other and arrived within a step of each other, that would be impressive. If you crossed intergalactic space for longer than complex human civilization has existed and arrived within 2 seconds, that is the universe being almost absurdly punctual. Somewhere, Newton would have raised an eyebrow. Einstein, perhaps, would have allowed himself a quiet smile. The detection was not just a measurement, it was an alarm bell for observatories around the world. Once the gravitational wave alert and the gamma ray burst were recognized as likely connected, astronomers moved quickly. Telescopes began searching the region of sky identified by LIGO and Virgo. They looked for a new point of light, something that had not been there before, something fading, something near a plausible host galaxy. Time mattered. The optical glow from a neutron star merger changes quickly. It can brighten and fade over days. Infrared emission can last longer, but the early hours are precious. Astronomy, which often deals in millions of years, suddenly had a schedule measured in minutes and hours. The cosmos had sent a message, and everyone had to check their calendars immediately. But this section of the story stays with the tremble itself, because without that first gravitational signal, the later search would have been different. Gamma ray bursts are detected regularly, but their positions can be uncertain, and many are far more distant. The gravitational wave signal told scientists that this event was relatively nearby by cosmic standards and likely involved neutron stars. It gave a distance estimate. It gave a sky region. It gave the physical identity of the source before any telescope saw the glow. That is the power of gravitational wave astronomy. It does not merely say that something bright happened. It tells us that massive objects moved in a particular way, with a particular rhythm under strong gravity. The name GW170817 carries the date inside it. GW for gravitational wave, 17 for 2017, 08 for August, 17 for the day. It is simple, practical, and not very glamorous. Scientific names often behave this way. They are not designed for bedtime wonder. They are designed so researchers can keep track of things without accidentally naming every discovery after a mythological animal or a biscuit. Yet once you know the story, the name becomes warm in its own way. GW170817 is not just a code. It is the day a ripple from 2 neutron stars reached Earth and began one of the fastest, broadest astronomical follow-up campaigns ever carried out. The tremble was tiny because gravitational waves interact very weakly with matter. This is both a difficulty and a gift. It makes them painfully hard to detect, but it also means they can travel across the universe almost untouched. Light can be absorbed by dust, scattered by gas, blocked by dense material, or shifted by interactions along the way. Gravitational waves simply pass through. They carry information from regions that light may not escape cleanly. They are like messages sealed so well that almost nothing can open them, including, inconveniently, our detectors unless we build them with remarkable care. When GW170817 passed through Earth, it did not choose the detectors. The wave crossed the whole planet. It passed through you, or through where you would have been if you were on the right part of Earth at the right time, just as it passed through mountains and oceans. The difference is that humans are not built to notice a fractional change in space-time. We notice warmth, pressure, sound, light, hunger, tiredness, the unpleasant discovery that there is no clean spoon. We do not notice when the distance across our body changes by less than a subatomic width. LIGO and Virgo were built to notice what bodies cannot. They extended human senses into a domain where the universe had always been active but previously hidden. There is a calming humility in that. We did not command the universe to be louder. We learned to listen more carefully. The signal was not adjusted for us. It was not amplified by nature for human convenience. It arrived as it was, faint, stretched by distance, carrying the imprint of a violent event softened into a whisper. Our achievement was not that we made the universe speak, but that we became able to hear a thing it had been saying all along. The data from the detectors was then turned into understanding. The waveform, the shape of the signal over time, was compared with theoretical models. Those models are built from general relativity and knowledge of compact binary systems. By matching the observed chirp to predicted waveforms, scientists inferred that the source involved 2 neutron stars. They estimated the masses. They measured the distance. They constrained the tidal deformability of the stars. They used the timing between detectors to locate the source on the sky. Every part of the tiny tremble became useful. The frequency told one piece of the story. The amplitude told another. The duration told another. Even the way the signal ended had meaning. For people outside the field, it can seem surprising that so much can be learned from such a small measurement. But astronomy often works this way. A dot of light can reveal a star's temperature through its colour. A dark line in a spectrum can reveal an element in a distant atmosphere. A repeated dip in brightness can reveal a planet crossing its star. A faint shift in frequency can reveal a galaxy moving away. The universe rarely hands us objects directly. It sends traces. Science is the art of turning traces into reliable stories. GW170817 was a trace in the length of laser arms, and from it came a story of 2 neutron stars, a distant galaxy, a gamma-ray burst, a kilonova, heavy elements, and a new era of astronomy. There is also something wonderful about the scale contrast. The source was 130 million light-years away. The detector arms were 4 kilometers long. The change being measured was smaller than a proton. The scientists were ordinary-sized humans sitting at computers. The event involved matter denser than atomic nuclei. The signal lasted about 100 seconds in the detectors. The journey took 130 million years. Everything about the story jumps between scales so quickly that the mind has to settle into it slowly. This is why it belongs in a quiet narration, not because it is small, but because it is too large to rush. If you're resting now, imagine the Earth as it was at that moment, turning beneath the sky. Cities were awake in some places and sleeping in others. People were commuting, eating, working, scrolling, making plans, worrying about small things, laughing at private jokes, not knowing that a message from another galaxy was passing through them. The detectors were doing what they were built to do. Laser beams ran down long vacuum arms. Mirrors hung in careful isolation. Computers watched the returning light. Then the pattern appeared. A rising chirp, a signal that matched the end of 2 neutron stars, a tiny tremble that had spent 130 million years becoming a discovery. To hear something as faint as GW170817, humanity had to build a very unusual kind of ear. Not an ear with a drum, a canal, and tiny bones, though those are already impressive enough, especially considering how often we use them to listen to kettle clicks and distant phone notifications. This ear had no soft tissue, no nerves, no familiar curve that could sit on the side of a head. It was made of laser light, suspended mirrors, long vacuum tunnels, supercomputers, careful engineering, and a level of patience that almost feels like a scientific form of meditation. It did not listen for sound in air. It listened for space itself changing length. That is what makes LIGO and Virgo so strange and so beautiful. They are observatories, but not the kind that look like the old pictures of astronomy, with a dome opening under a starry sky and a telescope tilting upward like a thoughtful metal sunflower. They do not collect starlight in the usual way. They do not make images of galaxies. They do not show spiral arms, glowing nebulae, or the gentle blue-white sparkle of young stars. Instead, they lie along the ground in long, straight arms, waiting for something almost impossible to notice. A gravitational wave passes through Earth, and for a tiny moment, the distance between mirrors changes. The machine measures that change. The universe has moved just a little, and the instrument says, very quietly I noticed, LIGO stands for Laser Interferometer Gravitational Wave Observatory. It is a practical name, but it does ask a lot from a sleepy listener, so let us unpack it gently. Laser, because laser light is used as the measuring tool. Interferometer, because the machine works by splitting light into 2 paths and recombining it, watching how the light waves interfere with one another. Gravitational wave, because the signal being searched for is not ordinary vibration, but a ripple in space-time. Observatory, because this is not merely a detector waiting for one lucky event. It is a new kind of astronomical instrument, a way of studying the universe through gravity itself. There are 2 LIGO sites in the United States. One is in Hanford, Washington, in a dry, wide landscape that looks, in photographs, almost as if the machine has been drawn onto the Earth with a ruler. The other is in Livingston, Louisiana, surrounded by a very different environment of forest and humidity. The 2 sites are far apart on purpose. A true gravitational wave will pass through both, separated by only milliseconds, depending on the direction from which the wave arrives. Local noise, however, usually will not appear the same way in both detectors. A truck near one site does not politely drive through the other site at the speed of light. A small earthquake, a gust of wind, or a bit of local machinery may bother one instrument, but it will not mimic the precise timing and pattern of a cosmic wave in a global network. Having more than one detector helps scientists tell the difference between the universe speaking and Earth clearing its throat. Each LIGO detector has 2 arms stretching at right angles, each 4 kilometers long. 4 kilometers is long enough that walking one arm would feel like a meaningful little outing, though perhaps not the most scenic one, unless you're deeply fond of vacuum tubes and precision infrastructure. Inside those arms, laser light travels back and forth between mirrors. The mirrors are not ordinary mirrors like the one above a sink, where you might check whether you look awake enough for the day. These are exquisitely polished, carefully coated, suspended test masses, isolated as much as possible from ground motion and thermal noise. They have to behave almost like free-floating objects, even while they are part of a machine sitting on a restless planet. The reason for the long arms is sensitivity. A gravitational wave changes distances by an incredibly tiny fraction. The longer the distance being measured, the more detectable that fractional change becomes. Still, the actual change is absurdly small. When a wave passes, one arm may stretch while the other squeezes, then the pattern reverses. The difference is far smaller than the width of an atom, smaller than a proton, so small that if you try to compare it to everyday objects simply give up and leave the conversation, and yet the detector is built to measure it. That is the marvel. It is not that the wave becomes large when it reaches Earth, it remains unbelievably faint. The machine becomes sensitive enough to meet it where it is. The basic idea of laser interferometry is calm in outline. A beam of laser light is split in 2. One beam travels down one arm, the other travels down the other arm. They bounce between mirrors and return to the center. When the beams recombine, their waves overlap. Light is a wave, and waves can add or cancel depending on how their peaks and troughs line up. If everything's arranged just right, the returning beams can cancel each other almost perfectly at a detector port, making darkness where there might otherwise be light. But if a gravitational wave passes through and changes the length of one arm relative to the other, even by a tiny amount, the returning light no longer cancels in exactly the same way. A little light appears where darkness was expected. That tiny change contains the signal. It is a lovely trick in the way that many great experimental ideas are lovely. Use light as a ruler. Split it. Send it on 2 journeys. Bring it back. Let the waves compare the paths for you. If space itself is stretched or squeezed, the light will know. Of course, saying it that way makes it sound almost easy, like assembling a shelf from instructions that only contain 3 steps. In reality, the machine has to fight an entire world of noise. The ground shakes, the air would interfere, so the beam paths must be kept in vacuum. The mirrors move for reasons that have nothing to do with distant neutron stars. Heat causes motion. Quantum effects disturb the light. Seismic vibrations creep upward. Even distant ocean waves can make the ground hum. The detector must reduce, measure, subtract, isolate, and understand all of this. It is less like listening in a quiet room and more like trying to hear a single snowflake land while standing beside a motorway during a thunderstorm, except the snowflake landed 130 million years ago. Virgo, the European detector near Pisa in Italy, joins this effort with its own long arms, each 3 kilometers in length. Virgo is also a laser interferometer, and like LIGO, it waits for passing gravitational waves to change the relative lengths of its arms. Its presence in the network is tremendously important. With only 2 detectors, a gravitational wave source can often be placed somewhere along a broad region of sky. Add a 3rd detector separated by a large distance and oriented differently, and the region can shrink. The network begins to triangulate, not in a perfectly simple way, but in the same broad spirit that our brains use timing differences between 2 ears to locate a sound. More listening points mean better direction. For GW 170817, Virgo's role was especially valuable. The signal was strong in the LIGO detectors and much weaker in Virgo, but that weakness was not a disappointment. It helped narrow the source location. Because Virgo was less sensitive to that particular direction and polarization of the wave at that moment, The absence of a strong Virgo signal became a clue. Science can be wonderfully counterintuitive this way. Sometimes not seeing much is exactly what helps you understand where to look. It is a little like hearing a muffled knock through one wall and a clear knock through another, then realizing the muffled wall has told you something important about the room. The collaboration between LIGO and Virgo turned GW170817 from a ripple in data into a target for telescopes. The detectors could not produce a beautiful photograph of the source. That was never their job. Their job was to say, a gravitational wave has arrived, it looks like 2 neutron stars, it came from roughly this region of the sky, and it is close enough by cosmic standards that other instruments may see something. That message was enough to wake up a whole network of observatories. The quiet machines listening for spacetime became the starting point for a worldwide search in light. This is where it helps to think of LIGO and Virgo not as isolated machines, but as part of a larger scientific nervous system. They collect data constantly. Automated systems scan the data for signals resembling predicted gravitational wave patterns. When a candidate appears, alerts can be sent to astronomers. Human experts check the data, estimate its reliability, and refine the sky map. Other observatories receive the information and decide where to point. In the case of GW170817, the gravitational wave alert was followed by the detection of a short gamma-ray burst. That combination made the event urgent. A gravitational signal from neutron stars plus gamma rays arriving almost at the same time meant there could be fading light to find. The instruments themselves look quiet because they must be quiet. Their long arms are not dramatic in the way a rocket launch is dramatic. There is no flame, no countdown, no bright plume rising into the sky. Much of the wonder is hidden in control rooms, vacuum systems, optics, suspension systems, calibration methods, and data pipelines. It is a stillness built by effort. The mirrors hang from complex suspension systems to protect them from vibration. The laser light must be stable. The length of the arms must be controlled. The environment must be monitored. The instrument must know the difference between a gravitational wave and a loose component, a passing disturbance, or some small local mischief. In a machine this sensitive, almost everything becomes loud. Even quantum physics joins the list of things to worry about. Light arrives in photons, and the statistical behavior of photons can create noise. The mirrors themselves can be affected by radiation pressure from the light. Thermal vibrations inside materials matter. The coatings on mirrors matter. The shape and purity of the laser beam matter. The detector is not just a large ruler. It is an entire ecosystem of precision, where each part must be understood because each part can whisper into the data. To hear spacetime, scientists first had to learn the many accents of their own machine. There is something almost soothing about that kind of engineering when you let yourself sit with it. It is careful, layered, repetitive, and exact. A gravitational wave detector is not built by one brilliant gesture. It is built through decades of improvements. Better mirrors, better lasers, better vacuum, better seismic isolation, better software, better models, better understanding of noise. The first versions of LIGO did not detect gravitational waves. That was not failure in the simple sense. It was preparation. The initial detectors proved technologies and methods. Then advanced LIGO came online with far greater sensitivity. Virgo was upgraded as well. The listening became sharper. The universe had not changed its volume. We had turned down our own noise. When people say that LIGO and Virgo listen to space-time, it is a metaphor, but a good one. Real listening is not just receiving sound. It is attention. It is filtering. It is recognizing a pattern against a background. In a crowded room, your brain can focus on one voice and ignore others. In a gravitational wave detector, the data analysis tries to identify the pattern of a cosmic event in the middle of seismic, thermal, quantum, and instrumental noise. Templates based on general relativity are compared with the data. The expected chirp from two compact objects has a shape. If the shape appears in more than one detector with the right timing, and if local causes can be ruled out, the signal becomes a candidate. It is a form of recognition. For neutron star mergers, the signal is especially rich. Because the objects are lighter than many detected black holes, they spend longer in the sensitive frequency range of ground-based detectors. GW170817 was heard for around 100 seconds. That may not sound long in ordinary life. 100 seconds is not even enough time to make tea properly if you are being serious about it. But in gravitational wave astronomy, it is a long, informative sweep. The stars orbited faster and faster and the signal rose. The detectors followed that rise. Each cycle added information. By the time the signal reached its final moments, scientists had a gravitational record of two compact objects spiraling together. The LIGO and Virgo machines do not experience wonder, of course. They do not lean back after a signal and say, "Well, that was remarkable." They record interference patterns, sensor readings, environmental monitors, calibration data, and streams of numbers. The wonder belongs to the humans who built them and interpreted them. Yet there is something poetic in the plainest possible sense about machines designed to notice what no person can feel. We have extended our senses before. Microscopes let us see the tiny. Telescopes let us see the distant. Radio dishes let us receive invisible wavelengths. Particle detectors reveal things that pass through us unnoticed. LIGO and Virgo extend us into geometry. They let us sense changes in the fabric by which distances exist. That phrase, the fabric of space-time, is often used because it gives us something to hold. But it can be misleading if taken too literally. Space-time is not a cloth floating in a larger room. It is the structure of space and time themselves. A gravitational wave is not space-time flapping like a bedsheet on a washing line. It is a propagating disturbance in the metric, the mathematical relationship that tells distances and times how to be measured. That may sound too technical for a sleepy night, so let's bring it back down. The key idea is simple enough. When a gravitational wave passes, it changes the distance between free objects in a rhythmic way. LIGO and Virgo measure those changes with light. The fact that these machines sit on Earth adds another layer of strangeness. Earth is not separate from the universe it studies. The detectors are not outside the system, calmly watching from some perfect platform. They are on a spinning planet orbiting a star inside a galaxy, moving through space while trying to measure ripples from far beyond. The planet itself is noisy, alive with weather, ocean motion, human activity and geological tremors. Yet from this imperfect platform with enough care, we can measure signals from merging neutron stars in another galaxy. Science does not require a perfect place. It requires knowing the imperfections well enough to work with them. There is a helpful humility in the way LIGO and Virgo confirm one another. A signal seen in one instrument alone is not enough. It might be real, but it needs context. When multiple detectors see compatible signals at the right times, confidence grows. The network becomes more than the sum of its parts. Each detector has its own orientation, sensitivity, and local environment. Together they can reject false alarms, estimate direction, and strengthen the physical interpretation. This is why gravitational wave astronomy is global by nature. The universe sends one ripple through the whole Earth, and widely separated instruments compare notes. For GW170817, that comparison was the beginning of a cascade. The gravitational wave signal identified the source as a binary neutron star merger. The timing across the detectors helped localize it. The gamma-ray detection added urgency. Optical telescopes soon found the fading source in NGC 4993. But before any telescope saw the glow, before anyone studied the colours of the kilonova, before heavy elements entered the discussion, LIGO and Virgo had done the quiet work. They had noticed the tiny stretching. They had turned a barely imaginable change in length into a cosmic alert. It is worth imagining the detector arms in the moment the wave passed. Laser light was already moving through them, bouncing between mirrors in vacuum. The mirrors were suspended, isolated, monitored. The electronics were recording. The data streams were flowing. Then the wave crossed the site. One arm's effective length shifted relative to the other. The interference pattern changed. The signal moved through the analysis systems. At another site, milliseconds apart, a related pattern appeared. Virgo's quieter response added its own clue. The machines did not know the source, but the pattern carried it. 2 neutron stars, 130 million light-years away, were written into the light returning from mirrors on Earth. This is not only astronomy. It is also a story about trust in delicate measurements. Nobody saw the arms stretch with their eyes. Nobody felt the ground rise in a cosmic swell. The evidence lived in calibrated data, in models, in statistical significance, in agreement between instruments, in consistency with a gamma-ray burst and later electromagnetic observations. Modern science often asks us to trust carefully built chains of reasoning rather than direct sensation. That can seem less romantic than looking through a telescope and seeing Saturn's rings. But it is its own kind of romance. It says that reality has layers too subtle for the body alone, and that with care, cooperation and mathematics, we can reach them. The quietness of LIGO and Virgo also fits the subject they study. Gravitational waves are not blocked easily. They do not crash into the detector and dump their energy like a wave hitting a seawall. They pass through almost untouched. A detector does not catch a gravitational wave in the way a net catches a fish. It experiences the waves passing and measures the effect. Afterward, the wave continues outward into the universe, carrying on, weaker still, passing through other stars, planets, dust and emptiness. The detector gets only a moment of interaction, a small signature, a trace. It must make that trace count. There is a strange gentleness in the idea that the signal did not stop with us. GW170817 passed through Earth and kept going. Long after it left our detectors, it continued travelling through space. Somewhere far beyond us, if there are other observers with their own impossible instruments, perhaps the same ripple will one day reach them too, weakened but still carrying its story. They may detect it and give it another name. They may not. The wave does not mind. It is simply the outward memory of a merger, expanding through the universe. For humans, though, the moment mattered. LIGO and Virgo turned a distant collision into something we could respond to. They were the quiet machines that let gravity become an astronomical messenger. They showed that the universe can be studied not only by what shines, but by how space-time moves. And in the case of GW170817, they did more than hear. They pointed the way. Their signal sent telescopes searching, and soon the story would shift from the invisible ripple to a visible spark, a small fading light in a distant galaxy. The first light did not come as a sunrise. It did not spread gently across a horizon or warm the side of a quiet planet. It arrived as a flash of gamma rays, brief and sharp, seen by instruments in space less than 2 seconds after the gravitational wave passed through Earth. That timing was so close, after a journey of about 130 million years, that it felt almost like the universe had sent 2 messages in the same envelope. First came the ripple in space-time, the deep gravitational trace of 2 neutron stars spiraling together. Then came the light, energetic and sudden, as if the collision had added a tiny note at the end saying, "Yes, look here too." For astronomers, that little flash changed everything. A gravitational wave signal alone was already extraordinary. It could tell them that massive objects had merged, that space-time had trembled, that something compact and violent had happened far away. But light gives different gifts. Light can show where the event happened in the sky. It can reveal the galaxy that hosted it. It can change colour as the debris cools. it can be split into a spectrum where the fingerprints of elements and temperatures and motions begin to appear. Gravity had carried the rhythm of the final orbit. Light would carry the story of the aftermath. Together, they were not simply two signals, they were two ways of knowing the same event. The gamma-ray flash was called GRB 170817A. GRB stands for gamma-ray burst, which is another of those scientific names that describes exactly what happened, while somehow sounding like a filing cabinet label. Gamma rays are the most energetic form of light, far beyond what human eyes can see. A gamma-ray burst can last only a fraction of a second or a few seconds, yet release an astonishing amount of energy. Long before GW 170817, astronomers had suspected that some short gamma-ray bursts were produced by merging neutron stars. The idea made sense. Put two ultra-dense stellar remnants together, let them collide, form a compact central object, launch material at high speed, and perhaps a narrow jet of radiation could burst outward. It was a strong theory, but theories in astronomy often wait patiently for the universe to provide the right demonstration. On August 17, 2017, the demonstration arrived. NASA's Fermi Gamma Ray Space Telescope detected the burst. The European Integral satellite saw it too. The burst was not especially bright compared with many gamma-ray bursts, but its timing made it unforgettable. It appeared about 1.7 seconds after the gravitational wave signal. That near coincidence was like hearing a distant door slam and then seeing a faint flash under it. One clue might be interesting. Two clues, arriving together, make everyone in the house sit up a little straighter. Of course, when astronomers sit up straighter, they do not usually run outside and point randomly at the sky, though one imagines the temptation must be there. The sky is enormous. A gravitational wave detector network gives a region, not a neat little pinprick. A gamma-ray detector can also have a broad localization. Together, LIGO, Virgo, Fermi and Integral narrowed the possibilities, but there was still a wide patch of sky to search. Somewhere inside that region, in or near a distant galaxy, a new source of light might be fading. The challenge was to find it before it changed too much. Astronomy, which so often seems to move at the pace of ancient starlight, suddenly became a race against a cooling ember. This was not a race with engines and shouting. It was a race of alerts, coordinates, sky maps, observatory schedules, daylight, weather, telescope access, and human decision. The gravitational wave alert went out. Astronomers around the world began checking where the source might be visible. Some telescopes were in daylight and had to wait. Some were under clouds. Some had the right sky, but not the right instrument. Some could cover wide regions quickly, while others could look deeply at smaller areas. The whole effort became a kind of global choreography, with observatories scattered across Earth and in space trying to catch a fading point of light before it slipped too far into the dark. Think of it like being told that somewhere in a large city one window is just lit up for the first time, and that it will fade over the next few nights. You are given a broad district, not an address. Many teams begin searching, comparing new images to old images, looking for anything that was not there before. A supernova, an asteroid, a variable star, a camera artifact, a reflection. The universe, like any busy place, has many things that can pretend to be important if you glance too quickly. The task was not merely to find a new dot, but to find the right new dot. The fact that Virgo had helped narrow the sky area made the search much more possible. The source region was still large by the standards of a single telescope image, but it was manageable enough for a coordinated campaign. Astronomers created lists of galaxies inside the region that were at distances consistent with the gravitational wave estimate. This was a clever way to search. If the signal came from around 130 million light-years away, then the counterpart was likely to be in a galaxy at roughly that distance. Instead of sweeping every empty part of the sky equally, observers could prioritize galaxies that might host the event. It was not unlike searching for a lost key by first checking the places where keys are known to gather, which in my experience includes pockets, tables, and the one bag you already checked twice. Because the event was in the southern sky, telescopes in Chile became especially important. Chile is one of the great observing places on Earth, with dry air, high mountains, and some of the world's most capable telescopes. As evening came there, teams were ready. The Swope telescope at Las Campanas Observatory played a historic role. A team using it found a new optical source near the galaxy, NGC 4993. It was bright enough to detect, close enough to the galaxy to be plausible, and absent from older images. The source was first reported as SSS-17A, and later became widely known as AT2017GFO. That little point of light was the visible counterpart to Geodbear 170817. The discovery was not just one team seeing one thing and everyone politely agreeing over biscuits. Other teams independently found the same transient soon after. This mattered. Independent confirmation is one of science's quiet comforts. When several observers, using different telescopes and methods, find the same new source in the same galaxy after the same gravitational wave alert, confidence grows. The chance that it is some unrelated object becomes smaller. The fading light near NGC 4993 became the target everyone had been hoping for. The gravitational wave had pointed the way, and the telescopes had found the glow. NGC 4993 itself is not a dramatic spiral like the Milky Way, with bright blue arms full of young stars. It is an older-looking galaxy, often described as an elliptical or lenticular galaxy, with shell-like features, a calm-looking host for such a violent event. That contrast is one of the small surprises in the story. We sometimes imagine cosmic explosions happening in wild star-forming regions, in bright blue nurseries where massive stars are being born and dying quickly. But neutron star mergers can happen long after the stars that made them have died. A pair of neutron stars may wander through time for millions or billions of years before merging. By the time they collide, they may be in an older galaxy, far from any obvious stellar nursery. The violence of the merger was not young and impatient. It was the delayed ending of a very old binary story. The light found near NGC 4993 was not like an ordinary supernova. It changed quickly. In the first observations, it was relatively blue, meaning hotter and brighter in shorter wavelengths. Over the next days, it reddened and faded, shifting toward infrared light as the debris expanded and cooled. This rapid colour change was one of the key signs that astronomers were seeing something different. A kilonova, as we will explore more deeply next, is powered by the radioactive decay of newly formed heavy elements in material ejected by a neutron star merger. But at this point in the hunt, the important thing was that the light behaved like a predicted counterpart to such a merger. It was not simply present, it was changing in the right way. There is a particular kind of beauty in fading light. A bright, steady star can feel eternal, even though it is not. A fading transient reveals time openly. It says, "Catch me now, because tomorrow I will be different." Astronomers watched GW 170817's optical counterpart hour by hour and night by night. They observed it in visible light, infrared, ultraviolet, X-rays, radio waves. Different wavelengths told different parts of the story. Early optical and ultraviolet observations showed the hot, fresh glow. Infrared observations became increasingly important as the light reddened. X-rays and radio waves appeared later, helping reveal how fast material was moving and how it interacted with its surroundings. The event was not one photograph, it was a developing story. In the hours after the detection, observatories began collecting data at a pace that was extraordinary for astronomy. Small telescopes, large telescopes, ground-based observatories, space telescopes, wide-field surveys, spectrographs, infrared instruments, high-energy satellites all joined in. It was a worldwide search and then a worldwide watch. The gravitational wave community and electromagnetic astronomy community, which had long prepared for such a moment, suddenly had a real event in common. There were emails, circulars, observing requests, quick analyses, sky maps, candidate lists, comparisons with archival images, and probably more caffeine than any circadian rhythm would recommend. Yet beneath the rush, the logic was simple and careful. Find new sources in the localization region. Check whether they are near galaxies at the right distance. Compare with old images to rule out known objects. Observe again to see whether they fade or change colour. Take spectra to learn what kind of object they might be. Share enough information quickly that others can follow up. In a field where discoveries can depend on being first, GW 170817 also showed the power of coordination. Many groups contributed different pieces, and the final scientific value came from the whole collection. The universe had sent a multi-messenger event, and humanity answered with a multi-telescope effort. The flash of gamma rays was brief, but the fading optical and infrared light became the main visible sign of the merger. If the gamma rays were like a camera flash in a dark room, the kilonova was the glowing ember left afterward. The gamma rays hinted at a jet or high-energy outflow. The optical counterpart showed material ejected into space. The infrared glow pointed toward heavy elements with complex atomic structures, which absorb and re-emit light in ways that make the event redden quickly. The details were complicated, and the models had to be refined, but the broad picture was thrilling. The same event that shook spacetime had also made light, and that light was rich with information. One of the most important emotional shifts in this part of the story is that the event became placeable. A gravitational wave can feel abstract. It passes through Earth as a tiny change in distance. It is real, but not visible. The gamma ray burst, too, can be a broad flash on a space telescope's detector. But once astronomers found the optical counterpart near NGC 4993, the event had a home. It was no longer just a signal. It was there, in that galaxy, offset from its centre, a fading point of light against the older glow of distant stars. Humans could point telescopes and say, that is where the neutron stars met. Not in a vague cosmic somewhere, but in a specific galaxy, in a specific patch of sky. That change matters. Astronomy often turns mystery into location. A comet becomes an orbit. A burst becomes a host galaxy. A signal becomes a point of light. Once you know where something happened, you can return to it, compare it, study its environment, and ask deeper questions. What kind of galaxy hosted it? How far from the centre did it occur? Was there star formation nearby? How old might the neutron star system have been? How much material was ejected? How fast did it move? Did it launch a jet toward us or slightly away from us? The fading light opened all of these questions. The search also showed how prepared the astronomical world had become. For years, astronomers had imagined what they would do if LIGO and Virgo detected a neutron-star merger. They had developed follow-up programs, wide-field surveys, galaxy catalogues, rapid communication systems, and theoretical models. GW 170817 was the test of all that preparation, and like many real tests, it was messier than the plan, but more rewarding than expected. The sky localization still covered a region. The event happened during daytime for some observatories. There were instrumental details, scheduling limitations, and the usual stubborn realities of weather and Earth's rotation. But the network worked. The light was found. The story moved from prediction to observation. It is also worth noting how human the urgency was. The merger itself had happened 130 million years earlier. Nothing anyone did on August 17, 2017 could change it. The light had already crossed the universe, and yet, from the perspective of observation, every hour mattered. The source was fading in our sky. The early colours were disappearing. The object was changing. Scientists were racing not against the event, but against the loss of information. That is a subtle kind of time pressure. The past had arrived, but it was arriving in layers, and those layers would not remain equally visible. The universe gives us ancient events in present moments, and we have to be ready when they unfold. For a listener settling into sleep, the image may be gentle, telescopes across Earth turning like quiet flowers toward one patch of sky. Some are small and quick, scanning. Some are enormous and deep, gathering faint light. Some sit under Chilean darkness. Some wait in space above the atmosphere. Some search in visible light. Some in infrared. Some in X-rays. Some in radio. All are following a clue left by gravity. A ripple came first. A flash followed. A fading ember appeared near an old galaxy. And around the world, people who study the sky understood that they were watching a new kind of event in real time. The light itself was not simply decoration after the gravitational wave. It solved problems that gravity alone could not. The gravitational wave gave a distance estimate, but the host galaxy gave an independent redshift, helping astronomers use the event as a new kind of cosmic distance marker. The light confirmed the link between neutron star mergers and at least some short gamma-ray bursts. The changing optical and infrared emissions supported the idea that neutron-rich debris from mergers creates heavy elements. The later afterglow helped reveal the structure of the jet and the material around it. Each wavelength added a page. Without the light, GW170817 would still have been a landmark. With the light, it became a library. This is the heart of multi-messenger astronomy. A messenger is not just a signal. It is a carrier of a certain kind of truth. Gravitational waves tell us about mass in motion, especially compact masses under strong gravity. Electromagnetic waves tell us about matter, temperature, magnetic fields, radiation, and chemistry. Neutrinos can tell us about nuclear processes and collapsing cores. Cosmic rays carry still other clues, though they are often bent by magnetic fields. When more than one messenger arrives from the same event, the universe becomes less like a silent painting and more like a scene with depth, sound, heat, and motion. GW170817 was the first time a binary neutron star merger gave us this combined view through gravitational waves and light. Still, one can imagine how ordinary the sky may have looked to anyone not using instruments. There was no visible explosion bright enough for casual stargazers to notice. No new star appeared to the naked eye. NGC 4993 is far beyond unaided human sight. The fading light was captured by telescopes, measured by detectors, analysed through software and compared with models. The drama was real, but not theatrical. It happened in faint pixels, data tables, spectra, and curves of brightness over time. Once again, the universe offered something enormous in a form that required care to recognise. That may be one of the quiet lessons of the whole event. We often expect important things to announce themselves loudly. In astronomy, they often arrive as a subtle change in a tiny patch of sky. A dot appears where no dot was. A signal rises where noise was. A spectrum turns red faster than expected. A detector records a slight stretch. Then slowly the meaning opens. 2 neutron stars merged. A short gamma-ray burst was launched. Heavy elements were made. Space-time rippled. Light followed. A new era began not with a shout, but with a faint transient near an old galaxy. As the observations continued, the source faded from blue to red, from visible brightness toward infrared warmth, and then gradually beyond easy reach. But before it vanished, telescopes gathered enough light to transform the detection into a physical story. The fading glow told astronomers that material had been thrown out from the merger. It told them that this material was expanding quickly. It told them that radioactive decay was heating the debris. It hinted that the debris contained heavy, complex elements. The first flash had brought attention. The fading light carried the deeper evidence. so we can picture the sequence again, slowly. 2 neutron stars spiral together in NGC 4993. Their final motion sends gravitational waves across space. Those waves reach Earth after 130 million years and pass through LIGO and Virgo. Less than 2 seconds later, gamma rays are detected by satellites. Alerts spread. Telescopes turn. The search begins. In Chile, a new point of light is found near NGC 4993. Other teams confirm it. Over the following hours and days, the light changes, reddens, fades, and reveals the nature of the explosion. What began as a tiny tremble becomes a visible ember. What began as a detection becomes a place, a glow, a galaxy, a story. The fading light near NGC 4993 was not just the afterglow of a crash, it was a furnace cooling in the dark. It was the visible sign that matter had been torn from 2 neutron stars and thrown into space. Hot, dense, fast, and filled with the raw ingredients needed for one of the universe's strangest kinds of chemistry. At first, the source looked blue and bright, a small new point of light near an old galaxy. Then, over the next hours and days, it changed. It faded quickly. It reddened. It shifted toward infrared light, as if the universe had lit a match and then covered it slowly with a warm red cloth. Astronomers had expected something like this from a neutron-star merger. They had given it a name before they had ever seen one so clearly with gravitational waves. They called it kilonova. The name sounds a little dramatic, and to be fair, the event earns it. A kilonova is not a normal nova, and it is not a normal supernova. It sits in its own special family of cosmic explosions, produced when compact objects such as neutron stars merge and eject material rich in neutrons. The kilo part originally suggested something about its brightness compared with a classical nova, though names in astronomy can have a way of aging into tradition rather than perfect accuracy. Still, it is a useful word because it tells us we're dealing with something between categories, something brief, powerful, and deeply connected to the making of heavy elements. A kilonova is not simply a flash. It is a sign that the periodic table is being extended in real time. To understand why, we need to return to those neutron stars themselves. A neutron star is already a place where ordinary matter has been pushed into an extreme state. The material inside is packed with neutrons, far beyond the density of anything we can hold or build on Earth. When 2 neutron stars spiral together, they do not merge as tidy little spheres. They pull on each other, they stretch, they heat, they tear. Some material is swallowed into the central remnant or into the disk around it, but some is flung outward. That ejected matter is the important part for the kilonova. It is not much compared with the mass of the stars themselves, but in human terms it is enormous. A small fraction of a solar mass is still a vast amount of material, and it is racing away at a significant fraction of the speed of light. Now imagine what kind of material that is. It is not ordinary gas drifting gently through space like a sleepy cloud. It is neutron-rich debris from the crushed remains of stars. It expands rapidly after being ejected. As it expands, the pressure and temperature change. Atomic nuclei begin capturing neutrons at incredible rates. This is the rapid neutron capture process, often called the R process, because even nuclear astrophysics appreciates a useful abbreviation. In the R process, atomic nuclei absorb neutrons faster than they can decay. They become heavier and heavier, stepping upward through the periodic table in a rush. Later, some of those unstable nuclei decay into more stable forms. Out of that rapid sequence come many of the heavy elements that ordinary stars struggle to make. This is one of the great problems in cosmic history. Where do the heaviest elements come from? Hydrogen and helium were made in the early universe. Stars fuse lighter elements into heavier ones, building carbon, oxygen, silicon and iron through their lives and deaths. Supernovae can make and scatter many elements as well, but the heaviest elements, The ones beyond iron that require huge numbers of neutrons in extreme conditions needed special explanation. Gold, platinum, uranium, and many rare heavy elements are not produced easily in calm stellar interiors. They require events where matter is flooded with neutrons quickly. For a long time, scientists suspected that neutron star mergers could be one of the universe's major sites for this process. GZW 170817 gave that idea a real object to study. That means the kilonova was not just pretty, it was evidence. It was a glowing sample of freshly processed cosmic debris, too far away to touch but close enough, in an astronomical sense, to measure. As the material expanded, the newly formed radioactive isotopes decayed. That radioactive decay released energy, heating the debris and making it shine. This is why the glow lasted for days instead of vanishing instantly with the gamma-ray flash. The kilonova light was powered by the slow settling of unstable nuclei, like countless tiny nuclear embers warming the expanding cloud. It is a strange thought, but a concrete one. The light from GW 170817 was produced because new heavy atoms were forming and decaying in the debris of dead stars. At first, the kilonova was bluer. That early blue light suggested that some of the ejected material had relatively lower opacity, meaning light could escape more easily. This material may have had fewer of the heaviest lanthanide elements, or it may have been affected by neutrinos from the hot remnant, changing the neutron richness of the ejector. That may sound like a very technical little sentence to tuck into a sleepy journey, so let us place it gently. Some of the debris was easier for light to pass through, and it glowed blue at first. Other debris was richer in heavier elements that are very good at blocking and reprocessing light. As that material dominated, the light became redder and moved into the infrared. The colour change was a clue to what the debris contained. Lanthanides are especially important here. They are a group of heavy elements with complex electron structures, which means they interact with light in complicated ways. Material rich in lanthanides can have very high opacity. It traps visible light and causes the glow to emerge more strongly in red and infrared wavelengths. So when astronomers watch the counterpart to GW 170817 quickly redden, it was not just a colour change, it was a fingerprint. It suggested that the debris contained heavy R-process material, the kind expected from neutron star mergers. The kilonova was not holding up a sign saying lanthanides here, but in astronomy, a changing light curve can be almost as talkative if you know how to read it. The word gold naturally draws attention. Humans have always treated gold as something special, partly because it is rare, partly because it does not tarnish easily, and partly because we are magpies with bank accounts. But in the universe, gold is not special because it is shiny. It is special because it is difficult to make. A gold nucleus contains many protons and even more neutrons. Building it requires an environment where nuclei can capture neutrons rapidly before they fall apart. A neutron star merger offers just such an environment. When GW 170817's kilonova was studied, it strengthened the case that mergers like this can produce heavy elements such as gold and platinum, then scatter them into space where they may eventually become part of new stars, planets, asteroids, and much later, rings, circuits, telescopes, and tiny treasured objects in human hands. We should be careful, though, in the calm, honest way science requires. Astronomers did not scoop up the debris of GW 170817 and count individual gold atoms. They did not receive a neat inventory from the universe, saying, 3 Earth masses of gold, some platinum, a little lanthanum, please sign here. The event was far too distant and complex for that. What scientists measured was the light and its evolution, then compared it with physical models of kilonova ejecta and our process nucleosynthesis. Those models showed that heavy elements were needed to explain the glow. Later observations and studies of the kilonova spectrum even identified specific lighter R process material, such as strontium, in the debris. The larger story is not a simple direct photograph of gold being made. It is a careful chain of evidence showing that the conditions and the light match the creation of heavy elements. That carefulness makes the discovery more impressive, not less. Science is at its best when it separates what we know directly from what we infer strongly. With GW 170817, the direct observations included gravitational waves, gamma rays, optical light, infrared light, X-rays, radio waves, and spectra. The inference, supported by models and the observed colours and fading, was that neutron-rich ejecta underwent R-process nucleosynthesis and created heavy elements. That is a long phrase, but it means something wonderfully simple at heart. Dead stars threw out neutron-rich matter, and that matter built heavy atoms while it glowed. The scale is hard to hold. The amount of heavy material produced in a single neutron star merger may be enormous compared with anything on Earth. Some estimates for GW 170817 like events suggest that the heavy element yield can be many Earth masses in total, though exact amounts depend on the model and the event. Even if only a portion becomes elements like gold or platinum, it is still a staggering production line. Not a mine, not a forge, not a factory, but a cosmic explosion where nuclear reactions build atoms at speeds and densities beyond anything human industry could approach. Somewhere in that expanding debris, atomic nuclei were climbing the periodic table faster than any chemistry classroom chart was ever meant to suggest. There is a lovely connection here between violence and quiet usefulness. The merger itself was catastrophic. Two compact remnants collided after ages of spiralling together. The conditions were extreme enough to bend spacetime strongly, launch gravitational waves, eject matter, and produce high-energy light. Yet the result of such violence over long enough time can be ordinary beauty. Heavy elements drift into interstellar space. They mix with gas. They become part of later generations of stars and planets. On a rocky world, billions of years later, those atoms may sit in the ground, in seawater, in minerals, or in living creatures in tiny amounts. They may become part of tools, art, medicine, electronics, or jewellery. The universe can take an event that would vaporize any nearby observer, and after enough time and distance, turn its products into something someone wears gently on a finger. This does not mean the gold on Earth came from GW 170817 itself. That event happened in another galaxy, and its material will not be arriving here for our local use, which is probably just as well, since cosmic debris delivery from another galaxy would be inconvenient. But events like it, in our own galaxy's past or in the smaller galaxies that helped build the Milky Way, likely contributed to the heavy elements that ended up in the cloud from which our solar system formed. Earth's gold and platinum atoms have ancient histories. Some may trace back to neutron star mergers. Some heavy elements may also come from rare kinds of supernovae or other extreme events. The full accounting is still an active scientific question, but GW 170817 showed with remarkable clarity that neutron star mergers are real heavy element factories. The kilonova glow was the receipt, if we want to use a very unromantic but useful comparison. You do not see the kitchen directly, but you see the meal arrive. You do not watch every nuclear reaction one by one, but you see the light powered by the radioactive decay of the products. The colours, brightness, and fading rate tell you about the ingredients. Early blue light, later red and infrared glow, rapid fading, broad spectral features, all of these were pieces of the same evidence. The universe had cooked something heavy. A kilonova also differs from a supernova in how it changes. A supernova can stay bright for weeks or months, powered by different processes, including radioactive decay of nickel and cobalt in many cases. A kilonova fades faster. Its ejecta are smaller in mass than a typical supernova's outer layers, but much richer in neutrons and heavy elements. Its light can shift quickly into the infrared because of the high opacity of lanthanides and other R-process material. For observers, This quick fading means that early detection is essential. If the telescopes had waited too long after GW 170817, many of the most useful clues would have been lost. The light was not only faint, it was changing its mind every night. That gives the event a certain urgency even now when we tell it calmly. The gravitational wave arrived. The gamma rays followed. The telescopes turned. The blue light was caught. The red light was followed. The infrared glow was measured. Each stage mattered. The kilonova was not a static object, like a planet calmly reflecting sunlight. It was a cooling, expanding cloud. Its temperature, opacity, and radioactive heating changed with time. Its story was written in a curve, not a still picture. Astronomers call these brightness changes light curves, and in the case of GW 170817, the light curves became one of the key ways to compare the event with kilonova models. Spectra added another layer. When astronomers take a spectrum, they spread light out by wavelength, turning a point of light into a kind of barcode of physics. In many stars, spectra show sharp lines from specific elements. In kilonovae, the situation is harder. The material is expanding rapidly, so spectral features are broadened and blended. Heavy elements have complex atomic structures, making their signatures difficult to identify. It is not like reading a clear label on a jar. It is more like trying to identify a song played very fast, underwater, by an orchestra that includes instruments no one has fully catalogued. Still, the spectral behaviour of GW 170817 supported the kilonova picture and later helped identify some specific R-process material. The difficulty itself tells us something. Heavy element-rich ejecta are complicated because heavy atoms interact with light in complicated ways. There is a nice humility in how the kilonova forced different sciences to work together. To understand it, astronomers needed general relativity for the merger and gravitational waves. They needed nuclear physics for the R process. They needed atomic physics to understand opacities and spectra. They needed radiative transfer to model how light moves through expanding debris. They needed telescope observations across wavelengths. They needed computer simulations of matter under extreme conditions. A little fading dot near NGC 4993 became a meeting point for many branches of science. It was small in the image and enormous in meaning. If you imagine the expanding debris, picture it not as a perfect smooth bubble, but as different kinds of outflow. Some material may have been flung out dynamically during the violent merger itself, especially in tidal tails and shocked regions. Other material may have come later from winds blowing off the hot accretion disk around the central remnant. Some parts may have been more neutron-rich than others. Some may have had higher opacity. Some may have moved faster. The observed kilonova likely came from multiple components, which is one reason the early blue light and later red light could both appear. The event was not one simple glowing shell. It was a layered aftermath. And yet, from far away, all that complexity blended into a tiny fading source. This is one of the recurring themes in astronomy. The whole physical drama becomes one dot. A star with storms and magnetism becomes one point of light. A galaxy with billions of stars becomes a faint smudge. A neutron-star merger with ejecta, jets, disks, heavy elements, and a central compact remnant becomes a transient near an old galaxy. The work of astronomy is to unfold the dot back into the drama. GW 170817 gave scientists enough messengers to do that better than ever before. There is also a deep time connection hidden in the heavy elements. The R process happens quickly, in seconds, inside expanding debris. But the consequences last for billions of years. Heavy atoms made in a merger can drift through space, mix with interstellar clouds and wait. Later, gravity gathers those clouds into new stars and planets. On a planet, chemistry begins. Rocks form. Oceans may appear. Life may arise. Civilizations may eventually dig those elements from the ground and wonder where they came from. The answer may involve an event like GW 170817, not as a direct parent in every case, but as part of the universe's general way of making rare ingredients. Seconds of nuclear creation can become billions of years of cosmic inheritance. That is why the phrase, "we are made of star stuff," lovely as it is, needs a few footnotes. Much of us comes from ordinary stellar processes and supernovae. The oxygen we breathe, the carbon in our bodies, the calcium in our bones, all have stellar histories. But the heaviest elements may owe a great deal to rarer, stranger events, neutron star mergers, and perhaps other extreme explosions. So we're not only made of star stuff. Some of the world around us may also be made of dead star collision stuff, which is less graceful on a mug but scientifically satisfying. The universe is not a single factory. It is a whole supply chain of creation, and neutron star mergers are one of its more dramatic departments. For the sleepy mind, the kilonova can be imagined as an ember fading in a far galaxy. At first it glows hot and blue, then it deepens into red and infrared. Around it, an old galaxy holds its steady background of stars. Inside the expanding cloud, unstable nuclei decay, releasing heat. Newly formed elements drift outward. The violent moment has passed, but its products are still glowing. Telescopes across Earth and in space follow the ember as it dims. Scientists compare its light to models, trying to understand how much material was ejected, how fast it moved, and what elements it contained. The glow is fading, but the information is rich. The word alchemy is often used for events like this, and it is easy to see why. Ancient alchemists dreamed of transforming one element into another, often hoping for gold. The universe actually does transform elements, though not in a quiet workshop with candles and mysterious symbols. It does it in stellar cores, supernovae, and neutron star mergers. It uses pressure, heat, gravity, neutrons, decay, and time. A kilonova is cosmic alchemy without the mysticism, though still with plenty of wonder. It shows nature changing the ingredients of matter under conditions so extreme that they almost feel invented, except the detectors, telescopes, and spectra tell us they are real. GW 170817 did not answer every question about heavy elements. Scientists still study how often neutron star mergers happen, how much material they eject, how yields vary from event to event, and how their contributions compare with other possible R-process sites. One merger cannot settle the entire history of the periodic table. The Milky Way has its own chemical history, shaped by many events across billions of years. Some very old stars contain R-process elements, raising questions about how early and how efficiently heavy elements were produced. The story is still being refined, but GW 170817 gave a firm, bright, fading anchor point. It showed a neutron star merger making a kilonova, and that kilonova behaving as expected from our process-rich ejector. In a way, that is enough to change how we feel about the periodic table. Those little boxes in a classroom are not just a list of substances, they are a map of cosmic events. Hydrogen whispers of the early universe. Carbon speaks of stellar interiors. Iron remembers massive stars and supernovae. Gold may carry the memory of neutron star collisions. Each element is not merely a material, it is a history. To hold a piece of gold is not to hold something separate from the cosmos. It is to hold matter that needed an extreme story before it could exist. That does not make a ring heavier in the hand, but it may make it heavier in meaning. For most of human history, astronomy was a story of looking. We looked up with bare eyes first, standing under dark skies and watching the moon change shape. The planets wander, the stars keep their patient arrangements, and the occasional comet arrive like a visitor who had not written ahead. Later, we built telescopes. Then we built better telescopes. We learned to collect more light than our eyes could gather. We learned that the Milky Way was made of stars, that the faint smudges in the sky were other galaxies, that nebulae were nurseries and graveyards, that planets circled other suns, and that space was much larger, older, and stranger than the human mind first expected. For centuries, to study the universe mostly meant to catch its light. That light came in more forms than our eyes could see. Visible light was only the small familiar window. Radio waves showed cold gas and spinning pulsars. Infrared light slipped through dusty regions where visible light could not pass easily. Ultraviolet light revealed hot young stars. X-rays and gamma rays pointed toward the most energetic places in the cosmos, around black holes, neutron stars, supernova remnants, and violent jets. Each new wavelength was like opening another sense. The universe did not only shine in starlight, it glowed, flashed, pulsed, and whispered across the whole electromagnetic spectrum. Still, it was light. Different colours, different energies, different instruments, but still electromagnetic radiation. Then gravitational waves changed the arrangement. They were not another kind of light. They did not belong on the same spectrum as radio waves or gamma rays. They were ripples in spacetime itself, made by the motion of massive objects under strong gravity. They carried a different sort of information. Light tells us about hot matter, atoms, magnetic fields, radiation, and surfaces. Gravitational waves tell us about mass moving through curved spacetime, especially compact objects such as black holes and neutron stars. They come from the bulk motion of the system itself. They are not painted on top of the event. They are part of the event's deepest structure. Before GW 170817, gravitational wave astronomy had already begun. LIGO had detected merging black holes, proving that the universe could be observed through ripples in spacetime. That alone was historic. Black holes had merged in the dark, and the detectors had heard their final chirps. But those black hole mergers did not come with a bright visible counterpart. They were mostly gravity speaking alone. No flash guided telescopes to a galaxy. No fading glow could be studied night after night. The detections were astonishing, but in a certain way they were also clean and quiet. Two black holes came together, sent out gravitational waves, and left behind a larger black hole. Gravity gave the message, and gravity carried most of the story. GW 170817 was different because it brought the old astronomy and the new astronomy together. First came the gravitational wave, then came gamma rays, then came the optical source near NGC 4993, then came ultraviolet, infrared, X-ray, and radio observations. It was as if the universe had taken one event and translated it into many languages at once. Gravity described the final spiral of the neutron stars. Gamma rays hinted at a high-energy burst. Visible and infrared light revealed the kilonova, the expanding debris, and the creation of heavy elements. Later radio and X-ray signals helped reveal the shape and motion of the outflow. No single messenger held the whole story. Together they turned a distant collision into one of the most complete astronomical events ever studied. This is what multi-messenger astronomy means. It is the study of the same cosmic event through different carriers of information. The messengers can include electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays. Each one travels differently, interacts differently, and tells a different part of the truth. A single messenger is useful. Two messengers are transformative. More than two can be extraordinary, though the universe does not always arrange itself around our ideal observing plans, which is inconsiderate but not surprising. With GW 170817, the key combination was gravitational waves and light. That combination was enough to change astronomy forever. It changed astronomy first by proving that gravitational wave alerts could lead to real objects in the sky. Before this, astronomers had prepared for the possibility. They had built follow-up programs. They had made galaxy catalogues. They had planned how to search large sky areas quickly. They had imagined the moment when a gravitational wave detector would send out an alert and telescopes would turn toward a fading counterpart. But there is a big difference between preparing for a thing and seeing it work. GW 170817 showed that the system could function. A gravitational wave signal could be detected, localized, communicated, and followed up. Telescopes could find the light. The light could confirm the source. The source could be studied across wavelengths. A plan became a working method. This may sound practical, and it is, but practical changes can be revolutionary. Astronomy is not only about new theories, it is also about new ways of finding things. When Galileo first turned a telescope to the sky, he did not simply add a few details to old star maps. He changed what could be known. When radio astronomy opened, it revealed pulsars, quasars, cold hydrogen gas, and structures invisible to optical telescopes. When X-ray astronomy developed, the violent high-energy universe came into view. Gravitational wave astronomy, combined with electromagnetic follow-up, did something similar. It opened a method for studying events that are both dark in their deepest motion and bright in their aftermath. With GW 170817, astronomers did not just know that a merger had happened. They knew where it happened. That was a huge step. A gravitational wave alone can give a distance estimate and a sky region, but the optical counterpart placed the event in NGC 4993. Once the host galaxy was identified, the event became anchored. Scientists could measure the galaxy's redshift. They could study the environment. They could compare the gravitational wave distance with the galaxy's motion away from us. They could ask how far from the galaxy's centre the merger occurred, what kind of stellar population surrounded it, and what that might say about how long the neutron star binary had existed before merging. A source without a host is powerful. A source with a host becomes much richer. It also changed our understanding of short gamma-ray bursts. For years, astronomers had suspected that at least some short gamma-ray bursts came from mergers involving neutron stars. The evidence was strong, but indirect. GW 170817 gave the clearest link yet. A binary neutron star merger produced a gravitational wave signal, and a short gamma-ray burst arrived almost immediately after. The burst was weaker than many classical short gamma-ray bursts, likely because we were not looking straight down the most powerful part of the jet. That detail became important. It suggested that some bursts may look faint not because they are intrinsically weak, but because of the viewing angle. The universe is not only what happens, it is also where we happen to be standing when we observe it. That viewing angle lesson became even clearer as later X-ray and radio observations came in. The afterglow did not behave as a simple on-axis jet would. Instead, the data supported the idea of a structured jet seen off-axis, or at least an outflow whose brightness changed as it interacted with surrounding material. This helped astronomers understand how neutron star mergers launch jets, how those jets move through debris, and why gamma-ray bursts can look different depending on direction. The gravitational waves told us the merger happened. The gamma rays told us a burst occurred. The later light told us how the outflow unfolded. Each message corrected and completed the others. GW 170817 also changed the study of heavy elements. Before the event, neutron star mergers were a leading candidate for producing many R-process elements, but a direct observational link was still needed. The kilonova provided that link. The rapidly fading light, the shift from blue to red, the infrared glow, and the modelling of neutron-rich ejecta all supported the idea that heavy elements were being formed. This was not just an answer to a small technical question. It reached into the origin of matter around us. Gold, platinum, uranium, and other heavy elements had always needed an extreme birthplace. GW 170817 showed one. It connected a gravitational wave signal to the periodic table. That is a remarkable bridge. From spacetime ripples to jewellery, from neutron star matter to atoms in a planet's crust. Another way this event changed astronomy was by giving scientists a new way to measure cosmic expansion. Because gravitational waves can provide a distance estimate directly from the signal, events like GW170817 can act as what scientists call standard sirens. The name is a playful cousin of standard candles, which are objects of known brightness used to measure distance. A standard siren does not rely on brightness in the same way. The gravitational wave signal itself carries information about distance. If astronomers also identify the host galaxy and measure its redshift, they can compare distance and recession speed to estimate the Hubble constant, the rate at which the nearby universe is expanding. GW170817 provided the first real demonstration of this method with a gravitational wave event and an electromagnetic counterpart. One event was not enough to settle debates about the exact value of the Hubble constant, but it showed that the method works. Future neutron star mergers with identified host galaxies could add independent measurements. This matters because current measurements of the Hubble constant from different methods do not perfectly agree. The tension may point to unknown systematic errors, or perhaps to new physics. Standard sirens offer another route, another way to ask the universe how fast it is expanding. Once again, one event opened a path. The event also tested fundamental physics. The gravitational waves and gamma rays travelled about 130 million light-years and arrived less than 2 seconds apart. This showed that gravitational waves and light travel at nearly the same speed over cosmic distances, at least to extraordinary precision. That simple fact ruled out or strongly constrained many alternative theories of gravity that predicted different speeds for gravitational waves. It also confirmed a key expectation of general relativity in a new way. The universe sent two messengers across an immense distance, and they arrived almost together. That timing was not just impressive, it was a measurement of how nature works. There is something almost amusing about how polite the universe was with that timing. After 130 million years of travel, a delay of less than 2 seconds is the kind of punctuality most train systems can only dream of. Of course, the exact delay includes physics at the source, not simply travel time. The gamma rays may have been produced slightly after the merger, depending on how the jet formed and escaped, but the near arrival still gave scientists a powerful constraint. Gravity and light had crossed intergalactic space side by side, and neither had wandered off for a long lunch. GW170817 also changed scientific culture, or at least revealed a version of it under pressure. The discovery involved thousands of scientists and many observatories. It required rapid communication between gravitational wave teams and electromagnetic astronomers. It required coordination, sharing, competition, cooperation, quick decisions, and careful follow-up. No single telescope could do everything. No single field could explain everything. The event was too rich for one instrument and too fast for slow isolation. It rewarded networks. It rewarded preparation. It rewarded people who had spent years thinking about what to do when the alert finally came. This is an important part of modern astronomy. The universe is too large and too varied for one kind of instrument to be enough. A radio telescope may see what an optical telescope misses. A gamma-ray satellite may catch the first flash before ground-based telescopes can respond. A gravitational wave detector may identify the hidden merger before the glow is found. A spectrum may reveal what an image cannot. A light curve may show what a single observation would hide. GW170817 became a kind of rehearsal that turned into the actual performance. It showed the value of a global multi-instrument approach. It also changed public imagination. Gravitational waves are abstract. Even when explained clearly, they are hard to picture. A ripple in spacetime sounds beautiful, but it can feel distant from ordinary experience. GW170817 gave people a story with more handles. Two neutron stars collided. The ripple reached Earth. A flash followed. Telescopes found a fading light. Heavy elements were made. Gold may come from events like this. The story connected deep physics to familiar matter. It made gravitational wave astronomy feel less like a private conversation between detectors and equations, and more like a new sense opening for everyone. That public connection matters because wonder often needs a doorway. Not everyone wants to begin with tensor equations, and honestly, even the tensors would probably appreciate a quiet evening off. But almost anyone can understand the idea of hearing and seeing the same event. Almost anyone can feel the strangeness of a message crossing 130 million years. Almost anyone can be moved by the idea that the elements in precious metals may be born in collisions between dead stars. GW 170817 gave gravitational wave astronomy a narrative shape. It let the science enter memory. For scientists, the event became a benchmark. Models of kilonovae could be tested against real data. Simulations of neutron star mergers could be compared with gravitational wave constraints and electromagnetic observations. The physics of jets, ejector, radioactive heating, opacity, and afterglows could be refined. The event became a reference point that future discoveries would be measured against. Was another kilonova brighter or fainter? Bluer or redder? Did it show gamma rays? Was the jet pointed toward us? How much mass was ejected? Did the host galaxy differ? Every future event would carry its own personality, but GW 170817 became the first full portrait of its kind. At the same time, the event reminded scientists how rare and precious complete observations can be. Not every neutron star merger will be nearby enough. Not every one will have a counterpart that is easy to find. Some will happen in parts of the sky hidden by daylight or bad weather for key telescopes. Some will be poorly localized. Some jets will point away. Some kilonovae will be faint. The universe does not schedule discoveries for maximum convenience, which is probably wise because if it did, astronomers would never sleep. GW 170817 was special because the detectors were operating. The signal was clear, the source was close enough, the sky region became searchable, and telescopes found the counterpart quickly. Many things had to go right. That does not make it lucky in a meaningless way. It makes it a reminder that discovery depends on readiness meeting chance. The neutron stars merged long before anyone on Earth built a detector. The signal arrived when LIGO and Virgo were sensitive enough to hear it. Fermi was watching. Telescopes were ready. Follow-up teams had plans. The counterpart appeared in a region where it could be found. Chance opened the door, but preparation walked through it. This pattern appears often in science. The unexpected arrives, and only those who have built the right tools can recognize it. Multimessenger astronomy also changes how we define an astronomical event. In older astronomy, an event might be a brightening in a telescope image. In gravitational wave astronomy, an event might be a waveform in detector data. In multi-messenger astronomy, the event becomes the union of all its signals. It is not just the chirp. It is not just the flash. It is not just the fading red glow. It is the physical source that produced all of them. That shift matters because it pushes astronomers to think in systems. What happened before the merger? What happened at the moment of collision? What material was ejected? What radiation escaped first? What glow followed? What later afterglow emerged? How do all the observations fit into one physical timeline? GW 170817 gave us such a timeline. The inspiral produced gravitational waves. The merger launched or enabled a short gamma ray burst. Ejected debris powered a kilonova. Outflows interacted with surrounding material, producing later emission. The host galaxy gave context. The distance and redshift allowed cosmological use. The heavy element signatures connected to nucleosynthesis. The near-simultaneous arrival of gravity and gamma rays tested gravity's speed. One event became many sciences braided together, not in an abstract way, but in measured data. This is why saying it changed astronomy forever is not an exaggeration. Some discoveries add a fact. This one added a method. It showed that gravitational wave detectors can act as triggers for telescopes. It showed that light can confirm and enrich gravitational wave sources. It showed that compact object mergers can be studied from before collision to long after it. It showed that cosmic explosions can be understood through a collaboration of messengers rather than a single signal. Once that method exists, astronomy cannot quite return to its older shape. The sky is no longer only something to be watched. It is something to be listened to, compared, coordinated, and read through several different messengers at once. There is also a deeper philosophical change, though we can keep it practical and not float away into abstraction. Human senses are limited. We see a narrow band of light. We hear pressure waves in air. We feel heat, touch, balance, and motion. The universe operates through many channels we cannot sense directly. Astronomy has always been the story of building extensions to ourselves. The telescope extended sight. The radio dish extended sight into invisible wavelengths. The neutrino detector extended us into ghostly particles. LIGO and Virgo extended us into spacetime strain. Multimessenger astronomy says that no single extension is enough. Reality is richer than one sense. GW 170817 made that richness undeniable. If astronomers had only seen the gamma ray burst, they might have known a short burst occurred, but not with the same certainty that it came from a neutron star merger. If they had only detected the gravitational wave, they would have known the merger occurred, but missed the detailed light from the ejector. If they had only found the optical transient without the gravitational wave, they might have debated its nature with less confidence. Together, the signals locked into place. Each messenger reduced the ambiguity of the others. That is the strength of the method. The event also encouraged new urgency in building better detectors and faster follow-up systems. More sensitive gravitational wave observatories can detect events farther away. More detectors in more locations can localize sources better. Faster alerts can help telescopes observe earlier. Wide-field optical surveys can scan large regions quickly. Infrared telescopes can catch the red glow of kilonovae. Radio and X-ray observatories can follow afterglows over weeks and months. Future discoveries will not simply repeat GW 170817. They will expand the sample, reveal diversity, and show which parts of the first event were typical and which were special. That last point is important. One event can change a field, but many events build a population. GW 170817 was the first clear example of its kind, but astronomers want more. They want neutron star mergers at different distances, with different masses, different viewing angles, different host galaxies, different ejector, different jets, perhaps some forming long-lived remnants, and others collapsing quickly into black holes. With enough events, patterns emerge. Rates become clearer. Heavy element production can be better estimated. The neutron star equation of state can be constrained more tightly. The Hubble constant can be measured with more precision. The first event opened the door. The future catalogue will let scientists walk through the rooms beyond it. Still, there is a reason we keep returning to GW 170817. First events carry a particular feeling. The first time a telescope showed mountains on the moon. The first pulsar. The first exoplanets. The first direct gravitational wave. The first neutron star merger heard in gravity and seen in light. They are not final answers. They are moments when a possibility becomes real. Before them, scientists may have strong theories and careful predictions. After them, there is a data point in the world. There is evidence you can return to. There is a signal, an image, a light curve, a spectrum, a paper trail, and a changed imagination. So when we think of the birth of multi-messenger astronomy through GW 170817, we can picture it as a meeting. Gravity arrived first with the memory of two neutron stars spiraling together. Gamma rays arrived almost immediately with a hint of a burst. Optical telescopes found the glow. Infrared light revealed the reddening debris. X-rays and radio waves continued the story later. The host galaxy gave the event an address. The kilonova gave it chemistry. The waveform gave it mass and motion. The timing gave it a test of gravity. Nothing stood alone. The discovery lived in the connections. As the fading light near NGC 4993 dimmed, the method it demonstrated became brighter. Astronomers had learned that a ripple in spacetime could begin a worldwide search, that a small transient in a distant galaxy could reveal heavy element creation, and that the universe could be understood more fully when different messengers were allowed to speak together. This was not just a new observation of an old kind of event, it was a new way of doing astronomy. And once you have heard the universe through gravity and seen it answer in light, the next question becomes impossible to resist. What else did GW 170817 teach us about the nature of neutron stars, the behaviour of gravity, and the speed at which the universe carries its deepest messages? By the time astronomers had followed the fading light, measured the glow, and connected the gravitational wave to a galaxy, GW 170817 had already become more than a discovery. It had become a lesson with many layers. It taught us about neutron stars, those city-sized remains of dead suns that hold matter in a state so dense and strange that even the best laboratories on Earth can only approach it from far away with equations and particle accelerators. It taught us about gravity, not as a simple pull, but as a messenger that can cross the universe carrying the rhythm of mass in motion. It taught us about light too, because the gamma rays, the optical glow, the infrared fading, the X-rays, and the radio afterglow all arrived as parts of the same story. And quietly, with almost no drama in the way the signal itself crossed Earth, it gave one of the most precise confirmations that gravitational waves and light travel at nearly the same speed. The gravitational waves from GW 170817 travelled for about 130 million years. The gamma rays from the same cosmic event arrived only about 1.7 seconds after the gravitational wave signal. Now, that small delay does not mean the two messengers were definitely released at exactly the same instant. Near the merger, the gamma rays had to be produced by physical processes involving a jet or high-energy outflow, and those processes may have taken a little time. Still, the arrival was astonishingly close. Over a journey so long that it began before humans existed, before our species, before our cities, before anyone looked at the sky and wondered whether gravity could ripple, the two messengers reached Earth almost together. If light and gravity had travelled at noticeably different speeds, 130 million years would have revealed the difference very clearly. They did not drift apart in any large way. They arrived nearly side by side. This mattered because some alternative ideas about gravity had suggested that gravitational waves might travel at speeds different from light. GW 170817 gave nature a very long racetrack. The starting area was a neutron star merger in another galaxy. The finish line was Earth. The gravitational waves and gamma rays crossed that immense distance, and their arrival times showed that gravity's waves move at essentially the speed of light, at least within incredibly tight limits. It was not just a victory lap for Einstein, though general relativity certainly did well. It was also a way of ruling out many possible modifications to gravity. Science often advances by narrowing the field of what can be true. GW 170817 did that. It said, in effect, if you want a new theory of gravity, it must survive this timing test. There is something satisfying about the simplicity of the result. No one had to travel to the source. No probe had to cross 130 million light-years, which is fortunate because even the most optimistic travel brochure would struggle with that itinerary. The universe itself sent the test. A merger happened. Gravity and light left the scene. Earth received both. The clocks compared them. From a delay of less than 2 seconds, scientists learned something about the fundamental structure of reality. That is a very efficient use of punctuality. The event also taught us about neutron stars in a way that ordinary telescopes alone could not. A neutron star is not merely small and heavy. It is matter pressed into an extreme condition. Deep inside, the density may exceed the density of an atomic nucleus. At those pressures, matter may behave in ways we do not yet fully understand. The particles may arrange themselves differently. Exotic states may appear. The material may be stiff, resisting compression, or softer, deforming more under gravity. Scientists describe this with the phrase equation of state, which means the relationship between pressure, density, and temperature inside the star. It is a dry phrase for a very dramatic question. What happens to matter when gravity squeezes it almost as hard as nature can squeeze without making a black hole? GW 170817 helped answer that question because the two neutron stars pulled on each other as they spiraled together. Just as the moon raises tides on Earth's oceans, each neutron star raised tides on the other. But these were not gentle ocean tides moving across beaches. These were distortions in ultra-dense stellar matter under extreme gravity. The amount of deformation is called tidal deformability. If neutron stars are larger and less compact, they deform more. If they are smaller and more compact, they deform less. That deformation slightly changes the gravitational wave signal. The final inspiral is not exactly the same as it would be for two point-like objects with no internal structure. Hidden inside the ripple is a clue about the star's interiors. This is one of those ideas that feels almost too clever, but it is real. We cannot open a neutron star. We cannot place one in a laboratory. We cannot gently tap it with a spoon and ask whether it sounds stiff, which is for the best because the spoon would have a short and difficult career. Instead, we listen to the gravitational waves from two neutron stars pulling each other apart in the final seconds before merger. From that signal, scientists infer how much the stars deformed. From the deformation, they constrain the possible sizes and internal stiffness of neutron stars. Gravity becomes a kind of scanner. The merger becomes a natural experiment. The waveform becomes a report from matter at impossible density. The results from GW 17817 helped rule out some extreme possibilities. If neutron stars had been too large and too easily deformed, the gravitational wave signal would have carried a stronger tidal imprint. If they had been too small or too stiff in certain ways, other parts of the multi-messenger evidence would become harder to reconcile. The exact details are still studied and refined, because neutron star physics is not a simple bedtime puzzle, with one neat answer hidden under the pillow. But the event gave real constraints. It suggested neutron star radii in the rough range of about 10 to 13 kilometers for typical masses, depending on the models and assumptions. Think about that for a moment. A star more massive than the Sun, only about the width of a large city. The numbers sound compact. The reality is almost absurdly dense. GW 170817 also taught us about what may happen after two neutron stars merge. This is not fully settled in every detail, which is part of the interest. The total mass of the system was high enough that the final remnant likely collapsed into a black hole. But whether it did so almost immediately or after briefly forming a hypermassive neutron star is an important question. A hypermassive neutron star would be a temporary object held up for a short time by rapid rotation, heat, and other effects before gravity wins. That brief survival, if it happened, could influence the ejector, the kilonova, and the formation of the gamma-ray burst. The aftermath is not simply a black box. It is a sequence of physical stages, each leaving traces in the light and gravitational wave interpretation. The gamma-ray burst itself gave another lesson. Before GW 170817, short gamma-ray bursts were strongly linked in theory to neutron star mergers, but this event provided the clearest direct connection. The burst was relatively faint compared with many short gamma-ray bursts. Later observations suggested that this may have been because the jet was not pointed directly at us. Jets are narrow, powerful outflows, and their appearance depends greatly on viewing angle. If you are looking down the jet, the burst can appear brilliant. If you're off to the side, the burst can look much weaker or perhaps be missed. GW170817 showed that a neutron star merger can produce a short gamma-ray burst even when we are not staring straight into the brightest part of the beam. That helps explain why these events can look different from one another. The radio and X-ray afterglow added to that picture. Over weeks and months, emission changed in ways that helped reveal a structured jet or outflow interacting with surrounding material. The event was not simply a 1-second flash and then silence. It continued to speak at longer wavelengths. That later afterglow told scientists how energy was moving outward, how the jet was shaped, and how it ploughed into the thin matter around the merger. Again, the lesson came from combining messengers. The gravitational wave told us the merger happened. Gamma rays told us high-energy radiation escaped. Optical and infrared light told us about the kilonova and heavy elements. Radio and X-rays told us about the outflow. The whole event behaved like a carefully layered investigation, except the suspect was 2 dead stars, and the evidence was spread across the universe. Then there is the distance lesson. Gravitational waves can act as what scientists call standard sirens. The name is a little playful. Astronomers already use standard candles, objects whose known brightness helps measure distance. A standard siren uses gravitational waves instead. The shape and strength of the gravitational wave signal give a distance estimate. If astronomers can identify the host galaxy and measure how fast that galaxy is moving away with the expansion of the universe, they can estimate the Hubble constant, the rate of cosmic expansion nearby. GW170817 was the first event where this method could be applied with an electromagnetic counterpart in a host galaxy. The first standard siren measurement from GW170817 was not precise enough to settle the modern debate over the Hubble constant, but it showed that the method works. This is important because the current measurements of the universe's expansion rate do not all agree perfectly. Measurements from the early universe and measurements from the nearby universe have produced a tension that scientists are still trying to understand. Standard sirens offer an independent route. They do not rely on the same distance ladder as many traditional methods. With more events like GW170817, astronomers may be able to make this measurement more precise, and perhaps help clarify whether the tension points to measurement issues or something deeper about cosmology. So, from one merger, we learned about gravity's speed, neutron star interiors, gamma-ray bursts, heavy element creation, jet structure, and cosmic expansion. That may sound like a lot for 2 small stars to handle, especially after already having the difficult job of being ultra-dense remnants of supernova. But this is what makes the event so powerful. It sat at the crossing point of many fields: general relativity, nuclear physics, high-energy astrophysics, cosmology, stellar evolution, and observational astronomy all found something useful in it. GW170817 was not a single answer. It was a meeting place for questions. It also taught us how much we still do not know. This is one of the best outcomes in science, though it can feel slightly impolite. A great discovery answers questions, and then it opens better ones. How common are neutron star mergers? How much heavy material does each one make? Do all neutron star mergers produce jets? How often are the jets pointed toward us? How stiff is neutron star matter at the highest densities? What exactly forms in the first milliseconds after merger? How quickly does the remnant collapse, if it collapses? How much can future gravitational wave detectors reveal about the merger itself, not just the inspiral? GW170817 gave us a strong first example, but one example cannot describe the full variety of nature. The universe is not known for repeating itself in exactly the same outfit. Future detections will expand the picture. More sensitive gravitational wave detectors will hear neutron star mergers farther away. A larger global network will localize them better. Telescopes such as wide-field optical surveys and infrared observatories will search more quickly for counterparts. Radio and X-ray follow-up will reveal afterglows. With enough events, scientists will compare masses, ejecta, host galaxies, kilonova colours, jet structures, and distances. The first clear multi-messenger neutron star merger was like hearing one sentence in a new language. Future events will give us conversation. Even so, that first sentence remains special. It told us that gravity and light can arrive together. It told us that two neutron stars can make a kilonova. It told us that the heaviest elements have a real birthplace in such collisions. It told us that space-time can guide telescopes to a fading light. It told us that the universe is not only visible but measurable in its deepest motions. And maybe most importantly, it changed the feeling of astronomical discovery. The cosmos was no longer simply out there, shining. It was also vibrating, ringing, carrying messages through the structure of distance and time. As we let those lessons settle, we can return to the human side of the story. On August 17th, 2017, most people on Earth went about ordinary lives. They made breakfast, answered emails, walked dogs, caught trains, lost keys, bought groceries, worried about things large and small, and maybe looked up at the sky without noticing anything different. A ripple from two neutron stars passed through the planet. A gamma-ray flash reached satellites. Telescopes turned. Scientists began sending alerts and checking data. Somewhere in all that ordinary human activity, a new kind of astronomy became real. There is something comforting about that. The universe can change our understanding without interrupting the small routines that make up a day. And now, after following the ripple, the flash, the fading glow, and the lessons, we can begin to let the story rest. GW 170817 was not the loudest event in the universe, not the brightest, not the closest, and not the only merger of its kind that has ever happened. Countless neutron star mergers must have occurred across cosmic history, many too far away, too faint or too poorly timed for us to study. But this one arrived when we were ready. That is part of its quiet magic. It happened long ago, but its message reached Earth after humanity had learned just enough to notice. We had built LIGO and Virgo. We had gamma-ray satellites in orbit. We had telescopes ready to search. We had theories waiting to be tested. We had the patience to take a tiny tremble seriously. There is a gentle humility in that readiness. Humans are small, and our instruments are fragile compared with stars. A neutron star would make a mockery of any material we can build. A black hole would not care how impressive our observatory looked in a brochure. A galaxy contains more stars than we can easily imagine. Yet small beings on a small planet can still learn. We do it by extending our senses. We build mirrors larger than eyes. We build antennas larger than ears. We build detectors that can feel space-time change by less than a proton's width. We do not become larger than the universe. We become more attentive. That may be the lasting emotional lesson of GW 170817. Listening matters. The universe had been sending gravitational waves long before LIGO existed. Neutron stars had been merging long before anyone knew what a neutron was. Heavy elements had been forming in cosmic violence long before anyone polished gold or named platinum. Gravity had always known how to carry a message. We were the ones who had to learn how to receive it. And when we finally did, the message was not only about faraway stars. It was about the possibility of understanding what once seemed unreachable. So, dear listener, we have travelled tonight from two neutron stars in a distant galaxy to the long arms of detectors on Earth, from a ripple in space-time to a flash of gamma rays, from a fading kilonova to the gold and platinum scattered through cosmic history. We have followed the first great moment when humanity heard a neutron star merger through gravity and saw its light, and we have seen how that event changed astronomy from a science of looking into a science of listening, watching, comparing, and gathering many messengers into one story. And here you are, a little farther along your own quiet timeline than when we began. Perhaps the room around you is darker now. Perhaps your thoughts have slowed a little. Perhaps some part of you is still picturing that old galaxy, NGC 4993, with one small point of light fading near it after a collision that happened before humans ever existed. It is strange, isn't it, how the universe can make us feel both tiny and included at the same time. Tiny, because the distances are enormous and the forces are beyond anything in daily life. Included, because the same universe that makes neutron stars also makes the elements beneath our feet, the atoms in our tools, and the curious minds that wonder where all of it came from. If you are still awake, I would love to ask you again, gently, where are you listening from tonight? What time is it where you are? Is the world outside your window quiet? Or is it still moving with traffic, voices, weather, and the soft clutter of human life? Somewhere above all of that, beyond the clouds if there are clouds, beyond the moon if it is up tonight, beyond the planets and the Milky Way, the deep universe is still carrying messages. Some are made of light, some are made of particles, some are ripples in space-time passing through galaxies, stars, planets, and sleeping rooms without a sound. The detectors are still listening. LIGO, Virgo, and other observatories continue to improve. Future instruments will hear farther, more clearly, and more often. There will be more neutron star mergers, more black hole mergers, perhaps stranger signals we do not yet know how to name. Some events will arrive with light. Some will remain dark. Some will point us toward heavy elements, some toward dense matter, some toward the behavior of gravity itself. Astronomy is no longer confined to the glow of the sky. It has become a wider kind of attention, one that waits for the universe to move in more than one way. That thought can be restful. Even while we sleep, the cosmos continues. Stars burn, pulsars turn, black holes orbit, galaxies drift. Somewhere 2 neutron stars may be circling closer together, losing energy one ripple at a time. Somewhere else, a signal from a merger that happened millions of years ago may already be crossing the dark between galaxies, heading toward Earth. Perhaps one day it will pass through our detectors and become another small chirp in the data, another alert, another set of telescopes turning toward a fading light. The universe is not finished speaking, and we are not finished learning how to listen. If this journey has brought you a little calm, or a little wonder, or simply a quiet place to rest your thoughts, I would be ever so grateful if you liked the video and subscribed. It helps this sleepy corner of science reach others who might also enjoy drifting through the universe at a gentler pace. And if someone you know could use a peaceful reminder that the cosmos is vast, strange, and somehow still connected to us, perhaps share this with them too. For now, let the story soften. Let the numbers become distant. 130 million light years, a delay of less than 2 seconds, stars heavier than the sun and smaller than a city, a wave too faint to feel, yet strong enough to change astronomy. A glow where heavy elements were born. All of it can rest together now, not as something to solve before sleep, but as something to carry lightly, like a small lamp in the mind. The next time you see a piece of gold or look at the night sky, or hear the word gravity, perhaps GW 170817 will be there in the background, not loudly, just quietly. A reminder that the universe has more than one voice, a reminder that even the faintest tremble can carry a story across deep time, a reminder that listening, when done carefully enough, can become a way of seeing. Sleep well, fellow traveller, wherever and whenever you are. The deep universe is still listening back in its own way, and somewhere far beyond the reach of ordinary sound, space-time is still rippling softly through the dark,